Hi, my name is Satyajit Pattnaik and I welcome you to this course on Convolutional Neural Networks. Now, what exactly is CNN? How different is it from ANN and RNN? Well, everything will be taught in this particular course. This course is all about convolutional neural networks and talking about the agenda. This is how the agenda looks like. We shall be first talking about the basics of deep learning. We'll try to understand what exactly is deep learning, what exactly is neural networks. We'll also be understanding what are the different activation functions that are available. Apart from that, we'll jump into how neural networks works and learns. After that, we'll be talking about some concepts like gradient descent and stochastic gradient descent that are one of the most important topics when it comes to deep learning. We'll also be talking about various concepts like forward propagation, backward propagation, and so on. Apart from that, we'll jump directly into CNN. What exactly is CNN? What type of problems do we solve in CNN? What are the different types of CNN do we have? CNN 1D, CNN 2D, CNN 3D. How do we build a CNN and evaluate a model? And last but not the least, we'll be talking about an end-to-end project. So, see you in the next video. Hi, in this video we shall be talking about understanding deep learning. What is the basic differences between machine learning and deep learning? And who created deep learning? So, before getting into the concepts of deep learning, before getting into understanding how neural networks work, let's try to give you a jinx of the pure basic things. Everybody know about AI, everybody knows about machine learning, right? Machine learning is nothing but an area of research through which you can achieve AI, you can achieve artificial intelligence. Now similarly, like machine learning is kind of a subset of AI, right? Very similarly, deep learning is a further subset of machine learning. But why do we need deep learning if we already have traditional algorithms like XGBoost, random forest, linear regression? Why do we need deep learning? Well, deep learning comes into picture for scenarios where machine learning fails, where machine learning algorithm fails. One very good example will be image classification. So when it comes to images, audio files or video files, analyzing those kind of data using machine learning or what do we call as classical machine learning algorithms is very difficult. So when your machine learning fails, then comes your deep learning. Doesn't matter, like for example, what people do is people directly jump into deep learning. Now if you are already getting a good results in your machine learning, there is no need of jumping into deep learning. So it all depends which scenario do you want to use what, but definitely in this particular course you will have a better understanding of what exactly is deep learning and how do we use multiple algorithms, multiple concepts like artificial neural network, convolutional neural networks to solve problems. So Geoffrey Hinton is called as the godfather of AI. He's called as the godfather of deep learning as well. He created the concepts of deep learning. Deep learning is nothing but it mimics the human brain. I'll give a simple example. I hope everybody knows that human brain is nothing but combination of neurons, right? Combination of neural networks. Very similar fashion, deep learning concepts also work. Deep learning concepts are very similar to how human brain works. A very easy and quick example, just imagine a newborn baby is born today or yesterday. When a newborn baby is born, he or she might not be able to spot a cat and identify that it's a cat, right? So what happens in real scenarios is that the child's mother regularly for the period of 6, 7 months, 8 months, 1 year, 2 years, she keeps on telling that this is a cat, this is a cat, this is a cat. If he or she spots a dog, her mom tells this is a dog. And that's how the child memorizes that This is a cat, this is a dog. Ultimately, after 1 year, after 2 years, if the child sees a cat or a dog, he or she will be able to identify it as a cat or a dog without any help from her mom. This is how her human brain works. Her brain is trained with multiple images of cats and dogs. Her mom has been training the child's brain again and again and again, and that's how the brain is matured, and he or she is able to identify whether it's a cat or a dog. Exactly similar fashion works with deep learning. The more amount of data you give to your model, the model keeps learning, and it becomes a model which will be able to give you good predictions. That's all about deep learning. Now, deep learning concepts comes into the picture where you have lots of data. You cannot simply create a model using just 2-3 images. Okay, well, there are some techniques. You can still use them to create a model with just 2-3 images or 10-50 images, but in general it's always recommended to have more data in order to build a deep learning model. Why? Because deep learning models are very expensive in nature. They take a lot of time in processing. They are computationally very expensive, memory wise also very expensive. So it is always recommended to have a very good configurations or very good type of data. That's all about deep learning, the basics of deep learning. Deep learning, as I already told you, it's a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain, called artificial neural networks. Why deep learning? I have already shown that in this image itself. The performance of deep learning is always better when you have more amount of data. Okay, now we'll also talk about some basic concepts. Probably in the next video, we'll talk about what is a neuron, how your different network layers looks like, input layer, hidden layer, and output layer looks like, and then we'll also talk about some future other topics in the future. That's all about this video. See you in the next video. Hi, let's get started with what is a neuron. Before talking about the neuron, let me show you the basic architecture of a neural networks. So if we try to draw how a neural network looks like, I'll draw probably here. Now just imagine these are some of your neurons, these are again your neurons, and these are again your neurons. So I have drawn somewhere around 8 neurons. Now these are your 3 different neurons from where your input comes. Okay, just imagine this is a basic neural network architecture. This is your input. Just imagine this neuron is nothing but x1, x2 and x3. What are x1, x2 and x3? If you remember machine learning, I hope you know what is x variables and what are y variables. X variables are nothing but our independent variables or the features. Let's say you are solving a problem like cats and dogs prediction or some sort of churn prediction. So your x1 could be your gender, this could be your geography, this could be your contract type. Just imagine these are just some features, right? These are your input variables. From here, this is how the network looks like. Okay, and from here there comes the output. This is where you get the output y hat, which is nothing but the predicted output. If I talk about this particular network, this is a very simple neural network. This is basically called as your input layer. This is basically called as your hidden layer. And this is basically called as your output layer. And your data moves from this to this direction, and from that direction also it moves to this direction, that we will be talking about in the forward propagation and backward propagation. But for the time being, let's assume it moves from left to right. From input, it goes through multiple hidden layers and then it predicts. This is how a general a general neural network looks like. Okay. Now we'll try to understand what is a neuron. A neuron simply is nothing but a basic building block. In this particular example, you can see there are x1, x2 and x3. Can you see there are something mentioned like W1, W2 and W3. What are these? These are nothing but weights assigned to each particular connection. What are weights? We'll be talking about that slowly. x1, x2 and x3. This green circle is nothing but your neuron, okay, where your summation of weights multiplied with inputs happens. x1, x2, x3 are also neurons and somewhat like that. So this is nothing but a very simple architecture where three inputs are coming, all the three inputs are being matched up together and they are combined with, they are multiplied with their weights and then they are added up. So basically what happens here is, if I simply draw and explain you, so these are your inputs. Just imagine these are your inputs, x1, x2 and x3. Okay. Now just imagine this is one of your neurons. Okay. This is your neuron. Now what will be the formula, or you can call it as a node as well. What will be the formula here? What is this value? Just assume the weights are W1, W2 and W3. What are weights? Weights are nothing but how strong the connection is. Let's say we three are friends, me, my best friend and another friend. Me and my best friend are very strong. We have very strong connection. So the weight will be more. Me with another friend, my connection is little bit not strong. So my weight will be less. As simple as that. Weights are nothing but how strong your connection is. That's it. For the time being, you can understand that. So the formula here will be very simple. It is nothing but summation of I equals to n to 1 to n 𝐓𝐢𝐸𝐿, which means in this case it will be W1 x1 plus W2 x2 plus W3 x3. So weights multiplied with your inputs and added up together. That basically is the formula. And what is this? This is your input layer. Very simple, right? Now, before going into activation functions, we'll also talk about the basic concepts of weights. What exactly is weight? Now, we talked about weights, right? So weights are parameters within our neural network that transforms input data within the network's hidden layers. Okay, simply if I talk about neural networks is nothing but a series of nodes or neurons. Within each node is a set of input, weights and biases. Now weights W is simply nothing but a parameter within a neural network that transforms input data within the neural network's hidden layers. Simple. Again, in simple terms, you can also call weights as they represent the strength of the connection between multiple units. Now, this is all about the weights and the neurons. What really happens here is when you move from one layer to another layer, of course, your weights and your inputs are multiplied together and added up, but they are also attached with some other thing. Let's say we call it as something multiplied with summation of 𝐓𝐢𝐸𝐸. Okay. So the output here will be, let's say we'll consider it as y hat. It's nothing but this. What is this? This is nothing but activation function. We call it as activation function. Now what is activation function? Again, we'll be talking about that in the next session or the next class, where we'll talk about multiple activation functions. But let me give you a small idea about activation functions. Activation function is an English word, simple activation function, which basically means whether you need to activate that node or not. So if your activation function is 0, that means this particular node is inactive. If this is not 0, then this particular node is active, right? If this node is inactive, that means the entire value of this node is 0. That means this node is passive, it's not turned on, right? Just imagine this way. If your elbow stops functioning, let's say your elbow stops functioning, it's paralyzed. That means the power here is 0, right? As simple as that. Similarly, in hidden layers or in any kind of neural networks, when you have activation function as 0, that means that particular node is turned off. It is passive in nature. How activation function works, which type of activation functions do we use in the hidden layers, that we will be talking about in the next class. How many types of activation functions are there, that also we will be covering in the next class. See you in the next class. We'll be talking about activation functions in this video. So what are activation functions? Activation functions simply are nothing but whether a node or a neuron should be activated or not based on a function, right? So what it does is it calculates the weighted sum of its input, right? So Wi multiplied with xi, weights multiplied with inputs. What it does is it adds bias to it. So it's nothing but Wixi plus bias. And then based on this particular function, it identifies, or it basically decides whether it should be fired or not. That's what the neuron does. And the firing capability, whether should be fired or not, depends on which activation function is used. Now in deep learning, there are multiple activation functions. So simply, if I have to explain, I will again take an example of a small paintbrush, and then I will try to explain. See, just imagine these are my inputs. This is my output, right? So here the formula will be very simple, right? Here the formula will be summation of Wixi. Just imagine there is a bias to it. There is a small error to it. So I have just added bias. Let's say we'll consider this as O1. So I will mark it as O1 is nothing but this Wixi plus bias. Imagine this way, in neural networks, each and every layer has a activation function. So let's say you are defining 10 hidden layers, there will be 10 activation functions. So here also there will be an activation function. If there are some other hidden layers, there will be activation functions. Based on the type of activation function, the node decides whether to be fired or not. Okay, right now, just understand this way. If you ask me which activation function to use in which scenario, that will definitely be taught with due course of time. Right now, just understand activation function is simply this. It calculates the weighted sum, add biases to it, and then decides whether to be fired or not. Very simple. Okay, so neuron doesn't know the bound of the value. This value could range from -infinity to infinity. So to activate or not, we use activation functions. There are multiple activation functions that we use. Some of them are step function. Let me write it down using this one. So some of them are step functions. We have linear functions. We have sigmoid functions. We have TanH functions. We have rectifier functions, or we call it as ReLu functions. So there are multiple activation functions that are available, and they have their own mathematics behind it. How these functions are created is a separate thing, which we will be covering slowly. In the next video, we shall be talking about step function, then linear function, then sigmoid, then TanH, and then ReLu. But what's more important is which function to use in which scenario. Okay, so these are the 5 different functions which we will be covering in this particular course. In the next session, we'll start with step function and so on. So these are the basics of activation function. I hope you understood what exactly is activation function. Simply, if somebody asks you what is an activation function, tell them that these are some functions which are a part of multiple layers which decides whether the neuron should be fired or not. And if they ask you more, simply help them understand using a small architecture. Just tell them if there are multiple weights assigned to it, what we do is we combine the weights along with the inputs, add bias. That's how the formula here looks like. We have an activation function attached to it, and this, based on the type of function we use, this value ranges from -infinity to infinity, and if it is 0, then that layer will be deactivated, the node will be deactivated. If it is not 0, then the nodes will be activated. Simple as that. That's all about this particular video on the basics of activation function. Next video, we shall be jumping into each type of them. See you. In the last video, we talked about activation functions. So far, many people might be thinking this way: what are we studying? What exactly are activation functions? We are getting confused. So trust me, let's try to go through each one of them slowly. We'll try to understand each one of them. Don't think anything about neural networks. Slowly, once we jump into the later part of this particular course, you will be able to relate what was taught and, oh, this is how it is to link it up. Because machine learning, deep learning is all about this. We learn so many things, so many links, and then we try to combine them, and that's how the knowledge increases, right? So in this video, we shall be talking more about step function. Now, what exactly is a step function? So if I talk about step function, let's say, let me get the presentation here. Okay, so let's consider a threshold based activation function. So just imagine we have a threshold. What is a threshold? Let's say I am having multiple people scores, and score ranges from 0 to 100. If I define a threshold called as 70, anybody beyond 70 have performed really well. Anybody below 70 have not performed well. That means I'm setting up a threshold, right? Similarly, step function is a threshold based function. So let's consider a threshold based activation function. If y is above a certain value, declare it as activated or not. Simple. Now, if I draw, this is how a step function looks like. So something like this. This is 0, this is 1. And in your, this is 0 and something like that. This is your y-axis and this is your output. Now you can see activation function A is equals to activated if y is greater than threshold, else not. Y is greater than threshold. Okay. Alternatively, A is 1 when y is greater than 0. Okay. Or else y is greater than the threshold. A is 0 otherwise. So whenever you can see beyond this part, your output is activated. This part, your neurons are not activated. So after a certain threshold, your neurons are getting activated. Before certain threshold, your neurons are not activated. That's the simplest answer to this step function. Where do we use step functions? Mostly step functions are used in binary classification problems. Binary classification problems where you have simple outputs. You have your input layer, something like this. This is your hidden layer and this is your output. Okay. Now if this is 1, that means neuron is activated. If this is 0, neuron is not activated. Why this function doesn't work on multiple classification problem, multiple class classification? Let's say you have multiple classes. What do you mean by multiple classes? Just imagine you are predicting, let's say we'll talk about a case study. Let's say churn prediction is a binary classification problem where you have classes like churned or not churned. Simple. So in binary classification problems, always there is one neuron in the output layer. Okay. Now if it is not binary, it is tertiary or multi-class. Let's say simple example is iris classification. Okay. You are predicting whether the type of flower is setosa, virginica or versicolor, if I am not wrong. Okay. Now in this kind of scenario, how many inputs do we have? Let's say petal width, petal length, sepal width, sepal length. There are 4 neurons and these are your hidden layers. I will not draw these hidden layers in depth. These are very messy networks. There are some hidden layers and there will be 3 neurons in the output. Okay. Okay. 3 neurons. This is your setosa, this is your versicolor and this is your virginica. In these kind of problems, if you use a step function, that means what if this is also activated, this is also activated. Now if this is activated, this is 1, this is activated, this is 1, this is not activated, this is 0. So your predictions are setosa and versicolor, right? So you will not be able to predict properly in these kind of scenarios. So step functions are not applicable for multi-class classification problems. If it is binary, let's say you just have 2 classes, setosa and versicolor. So in your output there will be just one neuron and based on that you will be able to identify. If it is fired, then it is setosa. If not fired, it is versicolor. Or else if it is fired, it is churned. If it is not fired, it is not churned. Something like that. Again, for the time being, just imagine this way, that step functions are threshold based function. Based on a certain threshold, it gets activated and doesn't get activated if it is below the threshold, simply. And the drawbacks of step function is very simple. It doesn't work on multi-class classification problem. That's all about this particular video on step function. In the next video, we shall be talking about linear function and then so on. There are so many other functions to talk about. See you. The second type of activation function is going to be linear function. Last class, we talked about step function, and in this video, we'll be talking about linear function. Now, what exactly is linear function? You can see on the screen, linear function is nothing but which is linear in nature. And we all know the formula of line is nothing but, just drag it here. The formula of line is y equals to mx plus c, right? Very simple formula. And if I draw a line like this, it basically says that, your x-axis and your y-axis, your both x and y-axis are linear in nature, which means when x is increasing, y is also increasing, right? This basically means the linear property of a function. Now, simply if I talk about y equals to mx plus c, now we all know what is c, we all know what is m. It's the slope and the intercept. Now just imagine c is 0. What if c is 0? Let's say y equals to mx. Now my c is 0. So how will the line look like? It will pass through the center location. Simple, because C is 0. Now how do we find this line? If you talk from a layman's point of view, it's very simple. You can just write down multiple values of x and try to find what will be the value of y here. If x is 0, y equals to 0. If x is 1, y equals to 1. Y equals to m, right? Now assuming m to be 1, if I assume m to be 1, this basically will be 45 degrees angle, right? If m is not 1, the line will still pass through. Let's say, we'll take an example. Y is equals to 2x. This is the line formula. How will the line look like? For x0, what is y? Y is going to be 0. For x1, y is going to be 2. For x2, y is going to be 4. Now x0, y0, this is the point. x1, y2, this is the point. x2, y4, this is the point. Now this is the line for y is equals to 2x. Similarly, y equals to mx will always pass through the center. So what will be the derivative of this function? Derivative of this function is nothing but 2. Derivative dy of dx when your y is equals to mx. The derivative is always going to be, it's always going to be 1. Sorry, my bad. It's always going to be m, right? So derivative of mx is always going to be m, because m is a constant. 5x is going to be 5, 10x is going to be 10. So derivative of mx is going to be always m, which means that gradient has no relationship with x. Now what is gradient? What is this term called as gradient? Now if I simply explain this topic, we'll talk about what is gradient. Just imagine a simple diagram. Let's say this is my point A, this is my point B. If I draw a line, let's say this is 2, 3 and this is 8, 6. Simple, linear in nature, x is increasing, y is increasing, simple. Now we'll talk about basic maths. How to find the distance between these particular points. Let's say this is A and this is B. The formula is going to be very simple. x1 minus x2 square plus y1 minus y2 square root over, right? Whatever it is. x1 is nothing but 2 minus 8 square plus 3 minus 6 square root over. Whatever it is, 6 square 36, 36 plus 18 root over, somewhere around 6 square 36, 3 square 9, 45 root over, somewhere around 6 point something. Okay, whatever it is, 45 root over would be around 49, 6.7 or 6.8. So that's going to be the distance AB. Now what is gradient? Simple definition of gradient is G, or gradient, is nothing but delta y divided by delta x. What is delta y? Delta y is nothing but change in y divided by change in x. So here what will be the change in y? If I draw a right angle triangle and I will name this point as O, change in y is nothing but OB divided by OA. What is OB? What will be this point? It will be 8, 3. So what will be OB? We will use this formula. OB is nothing but 8 minus 8 square plus 6 minus 3 square root over divided by 2 minus 8 square plus 3 minus 3 square root over, which is nothing but this is 0, this is 0, 3 square 9 root over 3 by 6, which is 0.5. So the gradient for this particular line is going to be 0.5, which means if I have a line like this, let's say I have a line like this, I have a line like this, and I have a line like this. Which one will have highest gradient? For this line, delta y is very less, right? So the gradient will be low. For this line also the gradient will be low. For this line the gradient will be high. Why? Just considering the blue line, delta y is greater than delta x, so gradient increases. So if the line is like this, the gradient increases. Like this, like this, like this, the gradient increases. If the line is towards your x-axis, then the gradient decreases. That is all about the gradient concept. Okay, now talking about the next concept is that why do we not use linear function? Mostly linear function is one of those activation functions which, of course, when it comes to activation functions, we'll learn about each and every type, but honestly speaking, practical applications, we don't use linear functions a lot. There are multiple reasons for it. The first reason is that it is linear in nature. Okay, what does that mean? That means linearity is one of those properties which is a mandatory requirement for using this particular activation function. What if your data sets or data points are non-linear in nature? So apart from that, as I already explained, that when it comes to your neural networks, let's say this is your new input layer, hidden layer, output layer, hidden layer, input layer, and output layer. Now if we start using linear functions in each and every hidden layer, then the function, the output is always linear in nature, right? So just imagine y equals to mx, and the next one, for let's say for this one it's y1, for this layer it is y2. Y2 is nothing but y1 multiplied with another weight. So we'll talk about this example. It will be a little bit confusing right now. So we'll talk about why linear functions, combination of linear function is always linear in nature, and why it is a problem. We'll talk about that. So let me give you a small example to explain that the combination of linear activation functions are always linear in nature, and hence that is one of the reasons we don't use linear functions a lot in the hidden layers. Now just take a small example. This is my input, these are my hidden layers, and this is my output. Simple architecture. Okay, simple architecture. I will name it as N1, N2, N4, N3, and I'll give them weights as W1, W2, okay, W1, W2, W3, W4, W5, W6, okay, something like that. Now what is this? This is x1, right? Now what will be the output here? The output here, which is N1, is nothing but W1 x1. Simple. What will be the output at N2? N2 is nothing but W2 x2. What will be the output here? N3 is nothing but W3 N1 multiplied with, added with W6 N2. W6 N2. Simple. This is linear in nature, right? This is in the format of y equals to mx. Simple. Is this linear in nature? As of now we don't know, but we'll try to solve it that it is linear in nature. Okay, now I will try to replace these values. So N3, let me write it here. N3 is equals to W3 N1. So N1 is W1 x1, W1 x1 plus W6 W2 x2. So this is nothing but W3 multiplied with W1 is a constant. So let's name it as Wx1, just a number, random number, or else just name it as M1 x1. This is also a constant number, 5 cross 3 15, something like that. M2 x2. You can see this is also in the format of linear relationships. Y equals to M1 x1 plus M2 x2. This is in this format. So this is also linear in nature. So no matter how many layers we have, if all the layers are linear in nature, the final activation function of last layer is nothing but a linear function. So that means these two layers or n layer can be replaced by a single layer, as the combination of linear functions is a linear function itself. So the simple example or simple explanation of linear functions is that we can use it in some hidden layers, but if we have multiple hidden layers, like 10 hidden layers, it is not advisable to use linear function in each and every layer, because you got my point. Multiple layers having linear function and one layer having linear function is almost similar. So there is no use of using multiple hidden layers. Okay, so that's all about linear function. We rarely use linear functions, so that is one of the reasons I'm focusing less on this particular topic. So just remember, in case you want to test it out how this function works, you can use it in one hidden layer, not more than that. That's an advice. That's it for linear function. In the next video we shall be talking about the more advanced activation functions like sigmoid, TanH and ReLu. See you. Hi, we shall be talking about sigmoid function in this video. Now, sigmoid function, we have to give more focus to this particular function, because the previous functions that we studied, which is step function, linear function, we don't use it very often, but sigmoid function, TanH and ReLu, these are going to be the best or the top 3 activation functions that we usually use in deep neural networks. Now, what exactly is a sigmoid function? First of all, looking at this graph, it is quite evident that this is not linear in nature. Okay, so non-linearity is one of the advantages of sigmoid function, which makes it quite clear that this is one of the best activation functions. Well, hold on, there are some drawbacks of this function as well, which we will be talking about in the later half of this video. But let's just talk about the function. What exactly is this function? So you can see one of the mostly used activation functions, and sigmoid functions are mostly used in output layers. There used to be a time where researchers used to use sigmoid functions in all the hidden layers and in output layers, but that was probably in 1980s or 1990s. Recently, after ReLu has come into the picture, rectifier activation function has come into the picture, ReLu is the first choice of anybody who works with deep neural networks, at least for the hidden layers. But for output layer, sigmoid function or softmax function are still the best. Now, what exactly is sigmoid function? You can see this graph, very simple graph. If I draw this graph, this is how the graph looks like. Okay, if I redraw it, something like this. Simple. Now this is my x-axis, this is my y-axis. So the formula of this graph is very simple. Y is equals to 1 by 1 plus e to the power of minus x. Okay, this is the activation function, and this is the formula of this particular activation function. This range always lies between, you can see, always lies between this quadrant and this quadrant. Okay, so the range of this function always lies between 0 to 1. Now notice this particular portion. Let me just draw it in red. Notice this particular portion. Now can you tell me what will be the gradient in this particular area? The gradient will be higher, right? Let me just talk about a small portion like this. This is my delta y, this is my delta x. So gradient in this area is higher, which means a small change in x can lead your values to either of these values or either of these axes, right? So a small change in x can have a larger impact on y. That's what I meant to say. So a small change in x can lead your activation function to be in the first quadrant or else to be in the second quadrant, something like that. So just imagine this way, that gradient in this particular area, the red box, is higher, okay, because the change in y is higher and the change in x is lower. Now talking about these areas, if I just enlarge it, something like this, here what will be the delta y? Delta y is very near to 0, right? So gradient is always decreasing and very near to 0. What does this means? This means when the gradient is 0, your neurons are going to a passive state. So that means in this particular graph, these are the areas where neurons goes into a passive state. These are the areas where neurons go into the active state. Simple. Now advantage of sigmoid function is very clear. Unlike linear functions or step functions which are linear in nature, sigmoid function is non-linear in nature. And it is always going to range between 0 to 1. That is also an advantage of a sigmoid function. Again, this is one of those functions which are mostly used in deep learning. Okay, towards either ends, that means in your blue areas, y values tends to respond very less as compared to the changes in x, which means the gradient is very small, which means network refuses to learn further or it drastically becomes slow. That's all about this function. Now what will be the derivative of this function? Now derivative of this function, you can probably take help of any online derivative tools like Math is Fun or calculatederivative.com. There are some websites where you can easily find the output of derivatives. So what is the derivative? I'll leave a question mark. I'll definitely talk about the derivative of sigmoid function in one of the future classes, because sigmoid function leads to a problem in deep learning as well. What is that problem? The problem is vanishing gradient problem. We'll talk more about that problem in one of my separate videos, and that was one of the reasons why ReLu came into picture. Before ReLu came into picture, I think ReLu was introduced in 2010 or 2011. I'm not pretty sure about the exact year, but before the invention of ReLu, each and every researcher used to use sigmoid function. Sigmoid function used to be their first choice, but now ReLu. Well, sigmoid function is still very important because a lot of mathematics, a lot of statistics is involved in sigmoid function. So this is also used in almost all the topics in machine learning and deep learning. Very important topic. So that's all about sigmoid activation function, when and where to use practically. We'll definitely talk about that in one of the future videos. That's it about this particular video. See you. Hi, in this video we shall be talking about TanH function. So previous video was all about sigmoid function. We understood y equals to 1 by 1 plus e to the power of minus x. Sigmoid function lies between 0 to 1. Everything is good. We also talked little bit about the drawbacks of sigmoid function, that way long back in 1980s, 1990s, when the neural networks started. Well, the neural networks concept started way back in 1970s, but talking about 1980s and 1990s, where researchers were just using one or two hidden layers because of the computational limitations, right? Nowadays we have systems with 32 GB memory, 1 terabytes of hard disk, i7 processors, and we are able to create neural networks of 10 hidden layers, 20 hidden layers, 40 hidden layers. But long back in 1980s, researchers were restricted to just one or two hidden layers, and that was one of the reasons why they were happy with sigmoid function or TanH function. They have its own demerits. Sigmoid function and TanH functions are probably not the best activation functions, but they're still used. There were some limitations because of which ReLu came into picture. Why ReLu came into picture, we'll talk about that in the next video, and we'll also talk about the exact problems that happens in deep learning neural networks, like vanishing gradient problem and exploding gradient problem, in another video. So let's not talk about that. Let's focus on the activation function. Let's try to understand what is TanH function. Now, simply the diagram is very simple. TanH function, so sigmoid looks like this, right? It lies in this quadrant and this quadrant. Okay, so the values also ranges between 0 to 1. Now TanH function lies something like this. So TanH function lies between -1 to 1, very similar to sigmoid function, but it lies, the y value ranges from -1 to 1. Okay, now what will be the formula of this? In sigmoid function it was y equals to 1 by 1 plus e to the power of -x. Here y is equals to 2 by 1 plus e to the power of -2x minus 1. Okay, looks very similar to sigmoid function, also known as scaled sigmoid function. Now the relationship between sigmoid and TanH, do we have a relationship? Yes. So TanH of x is nothing but 2 times sigmoid function of 2x minus 1. This is the relationship between TanH and sigmoid function. Now characteristics wise, very similar to sigmoid function, ranges from -1 to 1, and it is non-linear in nature. For the time being, this is more than enough for you to understand about TanH function. In the next video we shall be talking about ReLu, and then we'll talk about the future topics in the future videos. See you in the next video. Bye bye. Hi, we'll talk about ReLu function in this video. In the previous videos, we talked about sigmoid function and TanH function. This video is all about ReLu function. Now, let's try to understand this way, because you haven't known about the problems in deep neural networks. So for the time being, just assume that there are some problems in deep neural network, like vanishing gradient or exploding gradient problem, because of which researchers faced a lot of issues in past, and that's where ReLu came into picture. ReLu was introduced in 2011. If I just show you when was ReLu introduced, you can see the rectified linear unit or ReLu activation function was proposed by Nair and Hinton in 2010, but in 2011 it was officially announced and officially launched. If you know more about it, just try to search using these keywords on the web. You will definitely get this paper which talks more about ReLu, why it was introduced and all those things, so you can find more details about it. But nothing to worry about. I'll definitely explain everything about ReLu, what are the problems, so each and everything will be covered in this course. Don't worry about it. Now ReLu function is simply, okay, let me just explain ReLu function here itself. Okay, now ReLu looks like this. If I draw this graph, ReLu looks like this. Is this linear in nature? Because we talked about the linear activation function, we talked about sigmoid. We have been telling that when the function is non-linear, it is better. Is this linear or non-linear? Now, some people might think that it is linear in nature. Well, it is non-linear in nature. Why? Just assume right side part. Is it linear? Yes. If x increases, y increases. Assuming the left side part. Is it linear in nature? Yes. It is a straight line. But the overall properties of ReLu is non-linear. Why? Because if you look at the overall graph, it doesn't show you that it is linear in nature. In some point it is just dormant, in some point it is increasing. So the overall properties of ReLu is non-linear. So it is non-linear in nature. What will be the formula? Y, which is nothing but activation function, is nothing but mx. So if I talk about m equals to 1, in this case the values will always range between max of 0, x. The values will always range between this. That means if x is less than 0, y equals to 0. If x is greater than 0, y equals to x. So in short, this activation function can never be negative. It will always lie between 0 to x, so 0 to infinity. That is the range of this particular activation function. It is non-linear in nature and combinations are also non-linear. If you use ReLu function in each and every hidden layer, the combinations are also non-linear in nature. We can stack layers because it is non-linear in nature, right? Now imagine a very big neural networks. Let's say I'll draw a small example. And just imagine there are ... so many networks here, so many hidden layers. So these are your hidden layers, these are your input layers, and these are your output layers, right? Just imagine a very big neural network with a lots of neurons. Using a sigmoid function or TanH function will cause almost all neurons to activate in an analog way. Okay, that means almost all activation functions or all the activations will be processed to describe the output of a network. In other words, activations are dense, which makes a neural network even costlier. Because neural networks, on the day one itself we talked that neural networks or deep learning is very costly, computationally expensive, memory wise also expensive. So if you are able to solve using machine learning, don't come into deep learning. But deep learning is, as it is very expensive, so we have to take care of it. So deep learning networks are very expensive, very costly. Ideally, in this scenario, we want few neurons in a network to activate and thereby making the activation sparse. This is where ReLu gives us the benefit. So ReLu comes as a rescue. Does that mean ReLu is the best? Well, I don't know. ReLu might be a better solution as compared to sigmoid functions, at least for the hidden layers, but is it the best solution? We don't know. It's always hit and trial. Machine learning, deep learning, everything is hit and trial. Nobody can tell looking at the data that random forest is going to be the best for this data or XGBoost is going to be the best. No, nobody can tell you that. Machine learning and deep learning, most of the concepts are hit and trial. Somehow you will get an intuition what could be better, but nobody can tell you with guarantee that this is going to be the best. Okay, so ReLu definitely is better, but we don't know. Now talking about the graph. Okay, now let's talk about the left side of the graph. What will be the gradient? The gradient is 0. Why? Because delta y is 0. So the gradient is 0. That means there are no activations on the left side of the graph. That means the neurons goes into a passive state. Now this particular problem where the gradient becomes 0, because of which weights will not get adjusted during the descent. That means neurons which go into this state will stop responding to variations in input or error. Simply because gradient is 0 in this case, this problem of ReLu is called as leaky ReLu. Sorry, this is called as dying ReLu problem. Dying ReLu problem. Because the gradient is dying on the left side of the graph. Gradient is almost 0. That means the neurons are not getting activated. So this problem where your neurons or the network is not active, that problem is called as dying ReLu problem. Now what is the solution to it? Because dying ReLu problem causes several neurons to turn off. It becomes passive. What is the problem or how to get rid of this problem? To get rid of this problem, what we can simply do is, instead of this red line, what if it is not on the y-axis or it is not on the x-axis? It is something like this. So my new graph is something like this. So in this case, y is not 0. Instead of that, y is a very small number. Let's say 0.001x. So y is a very small number. It's not 0. That means the neurons are not completely passive. They are not. The gradient is not 0. It is near to 0 but not 0. Now this is a scenario where we define this scenario as leaky ReLu. Okay, so dying ReLu and leaky ReLu are one of those most important topics that are probably asked in interviews as well. Many people ask to make the gradient a non-zero term, we introduce this concept called as leaky ReLu. Now, honestly speaking, ReLu solves a lot of problems. Again, I'll not talk about the problems in this video. Problems are going to be talked about in some of the future videos, but I'll make sure everything is understood. So don't worry about if you're not able to relate why this is introduced and all those things. We'll try to cover that. That's all about ReLu. I hope you understood what is rectified, ReLu rectified, what was that? Rectified unit, right? Something like that. I again forgot. Okay, it was a rectified unit something. I just call it as a rectifier function. ReLu wiki. When was ReLu introduced? Yeah, rectified linear unit, my bad. So I keep forgetting this term, but yeah, I just call it as a rectifier function, rectifier activation function. So that's all about rectified linear unit ReLu. And in the next video, we shall be talking about some topics like backpropagation and forward propagation. And then we'll talk about the problems. And then we'll quickly jump into CNN. That's all about this particular video. See you in the next video. Bye-bye. Hi. In this video, we shall be talking about backpropagation and forward pass. Now, this is by far the most important concept in neural networks, because if you don't understand backpropagation and forward pass, you will not be able to understand anything in neural networks. So far, we have already understood what is a basic neuron, how does the neuron transfers the knowledge to different neurons, what are weights, and we also understood what are the different activation functions based on which our neurons get turned on or turned off. Simple. Now we will be talking about backward propagation and forward pass. Simply to explain this, I will be taking an example on Notepad. So let's try to see this way. I will be drawing a small graph. Just imagine I am talking about a problem, let's say customer churn prediction. Okay, let's say I'm analyzing customer churn prediction data. That means I want to predict whether a customer is going to be churned or not. And just imagine I have multiple features for this. There are features like age, there are features like tenure, and there are features like anything, contract type. These are the three features that are available. Now, let's try to understand how the neural network will look like. As we have three features, our input layer will have three neurons. Simple. Now, randomly, I'm just using 4 neurons in my hidden layers. And this is my output layer. Now, this is how the network looks like. Okay, and this is a basic network. This is your input. This is x1, x2 and x3. These are nothing but age, tenure and contract type. And this is your output, where you get whether a customer will be churned or not churned. As simple as that. Now, what exactly is forward pass and what is backward pass? Now, what happens in neural networks is that, just imagine, let me try to explain on the entire page because I need more space to explain. Now, just imagine this way. I have a data set of 10,000 records. Simple. Now we already know that we divide the data into training and test data. Simple. Now just imagine my training data has 8,000 records and my test data has 2,000 records. Okay. Now what will happen is, when I am training the data, that means 8,000 records has to be passed. Now, how does records pass in a neural network? Let me draw a better example, better diagram. I hoped that I will draw a better diagram, but somehow it is even worse than the first one. Anyways, now okay. Oh gosh, let me just redraw it again. So we already have a data, 10,000 records. My training data has 8,000 records and my test data has 2,000 records, right? I'll probably use this. Okay, now I will use this to copy paste and create my neurons. So this is my first neuron, this is my second neuron, and this is my third neuron. These are all my input neurons. Okay, and these are my hidden neurons. My bad. 2. This is the difficulty of a teacher when he tries to explain everything on the MS Paint or some whiteboard. Anyways, now just imagine these are your 3 features. What are these features? These features are age, tenure, contract type. So just imagine if there are more features, your input layer will have more neurons. Okay. Now each and every neuron is attached to each other. I have just drawn a single layer network. This is your input layer, this is your hidden layer, and this is your output layer. And this is where you get the output. Simple, looks better. Now just imagine, how does the training happen in neural networks? I already explained you this thing that when you initialize, when you create your neural networks, your weights are initialized. Let's say W1, W2. So just imagine multiple weights are there. W1, W2, W3, W4 and goes on. How many weights will be there? 4 into 3, 3, 4, 12, 4, 16 weights will be there. Okay. 3 neurons going to each of these 4 neurons. So 3 each, 3, 3, 3, 3, 12 and then for 13, 14, 15, 16. Simple. Now 16 weights are initialized for the first time. There is another concept called as batch size. Batch size. Now just imagine my batch size is 800. Randomly, I am giving this batch size as 800. What does this mean? This means when the first forward pass happens, that means when the first time the data goes into the neural networks, 800 records goes together. 800 record goes together. And then on 800 records, you get your predicted values where you already have the actual values, and you compare and you find the cost function. Simple. After finding the cost function, this is the first time your data is getting passed in the neural network. Definitely the cost function will be higher. Cost function is nothing but the error rate, right? So the cost function will definitely be higher. Now what neural network does is, neural network already knows what are the different weights that are assigned to each of these neurons. So what he does is, it tells that, hey, you know what, we just messed up. The cost function is too high, the error is too high. What we can do is we can traverse back. While traversing back, we will change the weights. Okay, the neural network knows very well which weights are which weights are provided with how much values. So while backpropagating, it updates the weight, updates this weight, update that weight, and it goes on. That process is called as backward propagation. And in the process of backward propagation, weights are updated. It's better to write it in text. In the process of backward propagation, weights are updated. Now your W1 is not W1 anymore. It has been changed to probably W1 dash. Initially if it was 5, now it is 4 or 6. We don't know. That's a black box. So this is the full flow of forward pass and backward pass. As the batch size is 800, that means in one batch 800 record goes and weights, cost function is calculated, and in the backward propagation weights are updated. This one flow of forward pass and backward pass is called as iteration. Better to write it again. So iterations. One complete forward pass plus backward pass. That is called as iteration. Terminology alert, right? So another terminology. How many iterations are required to complete a total training set? Training set is 8000. Batch size is 800. In one iteration, 800 records are trained. Backward propagation, weights are updated. Second batch comes in, another 800 records forward pass. Again, cost function is calculated. Again, backward pass, weights are updated, and this flow goes on. The number of iterations required to complete a full training cycle here is 10. 10 iterations, because 8000 divided by 800 is equals to 10. So 8 iterations basically completes a full training cycle. 10 iterations basically complete a full training cycle. That is called as epoch. Okay, another terminology alert, epoch. Epoch is the completion of a full training data points. Okay, that is known as epoch. Now we'll give you a small example to test your knowledge. So imagine my training data is 10,000, my batch size is 100, and I am running my model for 20 epochs. So how many iterations will be there? Let's try to solve it. For one epoch, how many iterations? For one epoch, it will be 10,000 divided by 100, which is 100 epochs, 100 iterations. So 20 epochs, 20 into 100, 2000 iterations. So 2000 iterations will be required for 20 epochs. Now what is the meaning of epoch and all these things? That we will be covering slowly, but I will give you a basic idea about epoch. Now just imagine what we do is, when we try to create a model, we run our model for multiple epochs. because epoch is nothing but a hyperparameter to a neural network. We don't know what is the right value of epoch. Imagine this way. Why do we run it again and again and again? Why do we run it in multiple epochs? Why? Just imagine this way. As I have already explained you this thing, that your neural networks exactly works like human brain. Now just imagine I will give you 1,000 images of me. Just imagine you are looking me for the first time. This is the first time you are watching me. Definitely you will not be able to recognize me when you see somewhere outside, right? Just imagine I will give you 1,000 images to you and I will tell you, can you memorize everything right now? Definitely you can memorize, but it will be for a shorter period of time. You might not be memorizing. After 5 days you might forget. So always what happens is, when we feed a deep neural networks, when we train a deep neural networks, we don't pass all the data together. Okay, what we pass is, we pass data in chunk. Slowly the neural network learns, and by the period of time it learns properly, it can start giving you good accuracy. So this is the entire explanation about forward pass and backward pass. Now let's try to understand theoretically what is the meaning of it. Randomly initialize the model with weights, which we have already discussed. Input your first observation or the first row of dataset in input layer. Forward propagation from left to right. Neurons are activated in a way that input of each neuron activation is limited by weights. Propagate till the final output layer. So you have to propagate till the final output layer, right? You have to propagate till the final output layer. Compare y hat to y. That means compare your predicted value with actual value. Try to find the cost function. Now backpropagate from right to left. The error is backpropagated. Weights are updated according to how they are responsible for the error. The learning rate decides how much we update the weights. There is another concept in neural networks called as learning rate. The exact example I just explained you, right? 1,000 images if I give you immediately, that means your learning rate will be very high. If your learning rate is very high, it is mostly seen that your memory is very less. That means you will memorize it immediately, you will be able to give good results, but down the line, after 5 days, 10 days, 20 days, your memory power will decrease. That is the reason why we study. If we have an exam tomorrow, we have to study for the whole year, right? It's not like we have the exam tomorrow and I just study today just for 2 hours the entire curriculum and I will be memorizing it. No, doesn't work. So it is always recommended to give your learning rate very less, so that your brain processes slowly, and then with the pace of slow, it will definitely learn more. Okay, so learning rate is also another concept, and repeat this step till we finalize a model, batch learning or reinforcement learning. That's all about this backpropagation and forward pass, and these are some other techniques. These are some basic concepts like the neuron, which we already covered, activation functions, how neural network works and learns, gradient descent and stochastic gradient descent, and backpropagation. However, you don't know what exactly is gradient descent. In the next video, I shall be talking about gradient descent and stochastic gradient descent, probably in depth, and then we'll quickly jump into the CNN part, which is the best part. That's it about this video. See you in the next video. In this video, we shall be talking about the gradient descent and stochastic gradient descent. Again, this class will be on a very theoretical concept. Once we start jumping into the code part, into the CNN part, you'll have more understanding on the gradient descent topics. We'll also talk about stochastic gradient descent. Now, what exactly is gradient? What is gradient? Simple terms, if I just try to explain this, let's say this is the line, right? And just imagine the coordinates of this line are 2, 3 and 8, 6. How many of you know about the formula of a line? The line's formula is y is equals to mx plus c, right? How to find distance between 2 points in mathematics? I'm pretty much sure you know this, but it's just that you might have forgotten. So the formula of a line, let's say I name it as a, b. The formula of line is nothing but x1 minus x2 square plus y1 minus y2 square root over, okay, which is 2 minus 8 square, which is 6 square, plus 3 square root over, which is 45 root over, which is around 6.7. So the distance between A and B is 6.7. Clear. Why am I talking about this? Because we will be talking about gradient as well. Now gradient is, the simplest explanation of gradient is nothing but change in y divided by change in x. Simplest definition. But what is change in y and change in x? Now we'll try to draw using let me draw a right angle triangle here. What will be the location of this particular point? It will be 8, 3. Okay. If you don't understand, take a pause, plot it in your notebook. You will be able to get it. It will be 8, 3. Okay. So what is, let me name it C. So what will be BC? Following this rule, BC will be 3. 8 minus 8 square plus 3 minus 6 square root over. 8 minus 8 square is cancelled out. 3 minus 6 square is 9. Root over is 3. What will be AC? 2 minus 8 square plus 3 minus 3 square root over, which will be 6. So the gradient here is nothing but 3 by 6, which is 0.5. But what it has to do with respect to gradient descent? Now, same type of example I'll take. What happens in neural networks is that when we run models, as I told you that, let's say this is your input, right? Forward pass, backward pass, forward pass, backward pass. It goes on, right? It depends on the number of epochs you are defining. It depends upon your batch size. So forward pass, backward pass, it goes on, right? And as we go on this process, weights are updated after every iteration. In every backpropagation, weights are updated. So data goes in, weights are updated, weights are initialized, cost function created, backpropagated. While backpropagation, weights are updated, new batch comes in, another forward pass, again cost function calculated, again backward propagation, weights are updated. It's a continuous process. What really happens is that if I draw cost function with respect to weights, when for the first time we are running the code, cost function will be very high, right? Somewhere here. Then the cost function decreases. So this is how the graph looks like. So cost function decreases. At this point of time, it is the lowest, but I don't know where to stop, right? And then immediately when it increases, when the cost function decreases and then increases, it basically understands that, oh, we have to again fall back to this back to the previous step, because that's where the cost function was lowest. Now cost function started increasing. Now this is the basic concept behind gradient descent. Gradient basically means your cost function is decreasing. Now gradient means change in y by change in x. Descent means decreasing. So the gradient keeps falling. Why? Consider this graph. In this area, your gradient is high, right? This is your delta y, this is your delta x. At this point of time, your gradient is almost 0. So you have to find that particular point, sweet spot, where your gradient is 0, right? Gradient descends. This is the classic example of gradient descent concept. Sometimes what we do is we might not use a very generic cost function. A generic cost function is y minus y hat square. Let's say you are not using this cost function. What happens in that case is, for example, your graph is something like this. So your cost function decreases at this point of time, and then it increases. You think that you should go back to the last location. This is the best point as per you, but no. You have to always keep on moving and run your model for a longer amount of epochs and longer amount of forward pass, backward pass, longer amount of iterations, so that you can actually find the global minima. In this particular example, this is called as stochastic gradient descent, where this particular point is called as local minima. You move ahead and this is the global minima. These are the two concepts of gradient descent and stochastic gradient descent. Now, what really happens in neural networks is that multiple things happen. Okay, either you can pass one record, or you can pass records in a batch, or else you can pass the entire training data. So there are multiple types of processes that happen. Batch learning happens, mini batch learning happens. So all this kind of learning happens in neural networks. These are the basic concepts of gradient descent and stochastic. Probably in the next video we shall be talking more about CNN models and rest of the things. That's it about this particular video. We'll see you in the next video. Bye. Coming on to the most important topic. What is CNN? Now, CNN is nothing but convolutional neural network. Convolutional neural networks. This is what CNN is. But what exactly CNN does? What exactly CNN does that artificial neural networks are not capable of? Now, just imagine this way. Let me give you a brief idea about deep learning. I hope if you have made till this part, you might already be knowing about machine learning properly, but just giving you an idea about it. Now, when you are dealing with flat files, let's say you are having text files or CSV files or Excel files. In that case, probably a better algorithm to use will be machine learning models, machine learning algorithms, which is otherwise called as classical machine learning algorithms. You can call your XGBoost, your decision trees, random forest, blah blah blah. Why do you need deep learning? The first prerequisite of deep learning is that if machine learning algorithm fails, then jump into deep learning. Else, don't. There is no requirement of trying out deep learning before even starting with machine learning. But there are some drawbacks of machine learning. Some of the drawbacks is that when it comes to images or voice data or videos, machine learning will not be able to process them. Who will be able to solve them? You would need CNN for that, convolutional neural network. So it could be images, voices or videos. We need CNN, convolutional neural network. So there are majorly three types of CNN. One is going to be CNN 1D, one is CNN 2D, and one is CNN 3D. 1D, of course, is one dimensional. That means your voice data will be able to be processed through a CNN 1D model. If you are dealing with images, you might need CNN 2D. If you are dealing with videos, you might need CNN 3D. But honestly speaking, most of our use cases going to any industry will be around CNN 2D. There are very few case studies or very few use cases in CNN 1D. I myself have my own research work in CNN 1D, but we will be majorly focusing on CNN 2D in this particular series. And CNN 3D is also not that important. Why? Because ultimately when you are using videos, Videos are nothing but combination of millions of frames, and those millions of frames are nothing but images. So you don't even need CNN 3D to process videos. You can also convert videos to your frames or images and use your CNN 2D models. That's the basic idea about CNN. Now, who is the man behind CNN? So CNN was 𝐓𝐢𝐦𝐞𝐋 is called as the godfather of CNN. Godfather of CNN. 𝐓𝐢𝐦𝐞𝐋. Now, he's the godfather of CNN. Now, what exactly is CNN? CNN is the deep neural networks model, or the deep neural networks, which basically takes an image or voice or video, assign them some learnable weights, and then process them. So before getting into the technicalities, let's try to talk about this image. Why this image is on this particular slide and we are talking about something else. Now let's try to talk about this particular image. Where is the person looking towards? Is he looking towards us, or is he looking towards the right side? Now definitely this is an illusional image, right? When your brain processes the illusional images, how does brain work? Brain considers some features, right? Some features that are already trained in your model, in your brain, and based on that it predicts. So if you simply place your fingers on top of the eye, let's say just ignore the eye. Now, if you just consider the nose and the lips, you could probably say that the person is looking towards the right side. But if you, let me just discard it. But let's say you are considering the eye as the first priority, or the eyebrows as the first priority, or the ear as the first priority, probably you could end up that and just ignore the nose part and the lips part. Probably you will think that the person is looking towards you. And this is exactly why and how our human brains also are processed. Similarly, when it comes to computers or the models, when we define our CNN models, based on these features, our CNN models are trained. So CNN is nothing but a neural network, and neural networks, from the first class itself I am telling that neural networks are nothing but it mimics your human brain, right? Take an example of a baby. When a baby is born, the baby will not be able to identify a cat or a dog. If he or she spots a cat, he or she will not be able to identify whether it's a cat or a dog. Her mom or the baby could be he or she, right? Let it be. Her mom is the one who teaches her, hey, it's a cat, it's a cat, it's a cat, it's a dog, this is a dog. And that's how the learning process starts from day one. She keeps learning. After some 6 months or 8 months or 1 year, the baby will be able to be predicting cats or dogs. Let's say the baby spots a cat, she will be identifying that this is a cat. Exactly the same fashion neural networks also work. Okay, now coming back to CNN. There are majorly 5 steps in CNN. First is convolution. Second is ReLu. Third is pooling. Fourth is flattening. Flattening, that means making it flat. And the fifth and the last will be fully connected layer. Fully connected layer. Convolution, ReLu, pooling, flattening, and fully connected layer. These are the major steps in the convolution system or in the CNN networks. What are each one of them? We will be covering in the next video in details using an example. So that's it about this video. We'll see you in the next video where we talk about more about the explanation of convolution, ReLu, and all these things. See you. In the last class, we talked about the basic concepts behind CNN. We also talked about the various steps like convolution, ReLu, pooling, flattening, and FCL, which is fully connected layer. But what do you mean by convolution? Convolution, because convolution is the main step, and that is what CNN is all about. CNN is all about convolution. But what exactly is convolution? Just imagine this way. We already know neural networks works exactly like our human brains, right? So convolution is one of the steps which is also called as a dimensionality reduction step. Dimensionality reduction step. What does that mean? That means in the step of convolution, we can reduce the number of features, but on the other hand, we keep the features intact. We keep the information intact. Now just imagine this way. We are dealing with images. Now you have an image like this. Let's say something like this. Some river is flowing, something like this. And how do we find what is the size of the image? Probably if you right click on any image, go to properties, you will be able to find the total size of the image and what is the total configuration of the image, right? So just imagine this way. Let me just not draw it. I'll quickly open a file. Now just imagine I have three images here. One is this, one is this. Okay. Now what is this image? This is a 1280 cross 720 pixels image, right? So 1280 cross, the first image is 1280 cross how much? 720. Okay, these many pixels are available in this image. How many pixels all total? See, before talking about this configuration, let me talk about the very basics, which I'm expecting you to know, but if you don't know, that's completely fine. Images are made up of pixels. Okay, when you say that my image is this cross this, which basically means internally your image has those many pixels. So in this image, how many pixels are available? 1280 cross 720, which is 921600 pixels. These many pixels are available. Okay, but okay, that's fine. But what is this image? Pixels are fine. I don't care about pixels. But what is this image? This image is showing me, this is a thumbnail image, right? Top 6 laptops for deep learning. I can see a laptop here or I can see a laptop here. So when you are spotting this image, you can probably identify this could be a thumbnail. What I can see is a text called top 6 in white. I see laptops for written in green. Deep learning has a background shape and we also see 2 laptops, right? When we resize this image, let's say we resize it to 300 cross 500. What is resizing? That means downgrading or upgrading, right? Let's say you downgrade this image exactly in this one. Here you have downgraded the image. What is the details? 500 cross 300. But what is the difference between this and this? Everything is same. Okay, the quality is not good here, but feature wise, it is the same, right? So similarly, if you want to take an example, we can quickly take an example of a live case study. Let's say dog image. Now this is a dog. Let me save it. You can see 800 cross 825, right? That is what the dog's configurations are. Let's say I will note it as dog 1. Done. Now this is my dog 1. Simple. What is the configuration of this one? 800 cross 825. Okay, let's just cancel everything. 800 cross 825. Simple. How many pixels? Around 64. Around this. Okay, I don't know the exact number. Something around this. These many pixels are available here. I am able to spot a dog, right? Now, let's try to take an online image resizer. What we will do? We will quickly, let's use this one. We will quickly give the image and we'll try to resize it. Let's say I want to resize it to 100 and 100. Resize image. Download resized image. Now this is the resized image. Can you spot whether it is a dog or a cat? Of course, yes, right? If I just zoom in, I can easily spot that it's a dog. The thing I'm going to explain here is convolution is exactly a step like this. Why do you have to pass a very high HD image to your networks? Because the more HD image you process in your networks, the more computational time it will be. So convolution is one of the steps which basically reduces the dimensions. But it is not exactly the same like this particular example which I explained. Here what I have shown you is I have just resized the image to a smaller configuration. This is exactly not convolution, but convolution somehow does dimensionality reduction. On top of that, there are some other features of convolution. Now, if convolution would have been this simple, I could have easily called any online tool and I could have done the convolution, right? Jokes apart. So, what exactly is convolution? We will be talking about it. So, after convolution, convolution is a dimensionality reduction technique. After convolution comes ReLu. What is ReLu? Again, a memory refresher. ReLu is nothing but ReLu is nothing but, let's say this is my graph and I'll just change my ink to blue. This is ReLu, right? Y is equals to max of 0, x. What does this mean? This means if x is less than 0, y is equals to 0. If x is greater than 0, y equals to x. This is all about ReLu, right? So by default, we will be using ReLu in CNN. We don't use any other activation layers. After ReLu comes pooling. Pooling is again another convolution. It's not a convolution step, my bad. It is again another dimensionality reduction technique. But what is pooling? Pooling is simply, just imagine this thing. You have an image. You pass pooling to it. Pooling will basically tell you most amount of information is in this area, this area, this area, this area, this area, this area, this or this. So it basically takes your image, like the output of your convolution, you pass your pooling. Pooling basically scans area by area and it will tell you, oh, this is where most of your information is. And pooling is also a dimensionality reduction technique. There are majorly 4 types of pooling as per Keras notebooks. You can quickly go ahead and check out the Keras documentation. So there is max pooling, there is average pooling, there is global max pooling, and there is global average pooling. These are the 4 types of pooling techniques that are available. What are each one of them? We will slowly discuss in the next class. After pooling comes your flattening. Now, refresher again. How does our neural network looks like? Our neural network is something like this, right? But this is not how our convolution neural network looks like. Convolution looks like this. Our neural network looks like this. da 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 da, our convolution neural network looks like this. So you have your input, this is your input, then comes your convolution step, then comes your pooling step, then comes your again pooling. So this is basically your multiple hidden layers. Then comes your flattening step. Then after flattening, you are converting it into fully connected layer, and then it goes to your output. This is how CNN network looks like. Okay. Now, what is flattening? You can see after this flattening, after this particular part, it is getting converted into this particular type, right? Neurons. So basically what happens is, just imagine if this is your final output of pooling. Just imagine this. 1, 2, 3, 5, 6, 7, 3, 2, 1. This is your final output of pooling. When you flatten it, it basically becomes a one-dimensional format. So it becomes 1, 2, 3, 5, 6, 7, 3, 2, 1. Why? Because only when it is in this format, then only it can be converged to this format, right? So flattening is nothing but flattening. You just flatten it. That's it. Very simple. And then fully connected, and then it will be calling the final output layer, which will be predicting. Now here in this example, this is probably a multi-class classification problem, because your digits could be from 1, 2, 3, 0, 1, 2, 3 till 9, right? So there are 10 classes. That is the reason there are 10 neurons in the output layer. So if you are passing input 2, you will probably get a more higher accuracy here. Let's say your outputs are like this, 0.05. This is highest, then you will predict, oh, this could be 2. This is all about CNN. I'm just discarding it. That is all about CNN. The explanation, the example part, using an example basically, will be taught in the next video. That's it. See you in the next video. Till then, bye bye. Hi, in this video we shall be talking more about the explanation behind CNN, how each step works. Now we already know the steps. The different steps are convolution. Then comes ReLu, then comes pooling, then comes flattening, and then comes fully connected layer. But what exactly do they do internally? We'll try to understand that in this particular video. So for an example, we will be considering this particular image. Now, what is an image? Image is nothing but combination of multiple pixels. And when it comes to pixels, pixels range from 0 to 255. If you talk about pixel ranges from 0 to 255, where 0 is black and 255 is white. That means the lower the value, it is probably darker image or a darker pixel. 255 or closer to that, lighter pixel. Simple. Okay. 0 is dark or black and 1 is white. Okay. So I have randomly provided some numbers here. That means just imagine this is a 7x7 image which has 49 pixels. Simple. This particular image is a 7x7 image. It has 49 pixels. Now, in order to perform the convolution step, the first step is to define a feature detector. Now, what is a feature detector? Let's try to understand. In CNN, there is a concept called as feature detector. Feature detector is simply something which detects the features. As simple as that. There is no better explanation for that. The other names of feature detectors are, it is also called as filters. It is also called as kernels. Now, in this example, I have defined a 3x3 feature detector. Why 3 cross 3? I don't know. I have just given an example. Logically speaking, when it comes to real-time scenarios, we usually go for an odd filter only. Okay, we never use even filters. Even in a lot of research papers you can go through, there are some specific explanations of using odd filters, but that we will be not covering in this video. So just imagine that we always use odd filters. That means 3 cross 3 or 5 cross 5 or 7 cross 7. So I have defined a 3 cross 3 matrix. What are these numbers? 1, -1, 1, 0, 1. I don't know. Our task as a researcher or as a data scientist or as a deep learning expert while implementing a CNN will be to introduce feature detectors. The values within feature detectors are basically black box. They are automatically created. Okay. And in real scenarios, we don't define just one feature detector. Imagine this way, that this is your image, right? This is a small feature detector. So this basically goes through the image like this, like this, like this, and it tells you that, oh, this is where, most amount of information is there. This is where information is there. No information, here information. But can we rely on this feature detector? The answer is no. So we define multiple feature detectors. So again, normally speaking, the thumb rule behind creating number of feature detectors is we define 2 to the power of n format. So when you are starting implementing your first CNN code, probably start with 32 filters and you can slowly increase the numbers. So the numbers you increase, maybe 32, 64, 128, your model becomes complex and complex. Okay, that's all about your feature detectors. So right now I'm just taking one example of feature detector and I will show you how this feature detector works. Now we have this feature detector. What happens here is, just imagine you have your input image, you have your feature detector. Feature detector is not just one, there are multiple. Okay, I'm just taking one example so that you understand how the process works. Simple. So how feature detector works? When you have a 7 cross 7 image and you are running a feature detector, your output has to be a reduced version of the same image. So logically speaking, here your output will be a 5 cross 5 matrix. How? Let's try to solve it. So first 3 cross 3 block is this part, right? Now here if I start multiplying the blocks, first block multiplied with the first block, so it's nothing but 0 multiplied with 1 plus second block multiplied with second block, 0 multiplied with 0 plus, and this goes on. So 0 multiplied with 1 is 0, 0, 0, 0, minus 2, 0, 0, 0, 1. So minus 2 plus 1, which will be minus 1. Okay. Similarly, we will move 1 pixel to the right side and 1 pixel to the bottom. Let's move one by one. Let's move 1 pixel to the right side. Now this is your new area right now. Feature detector again goes on it. So again multiplication happens. 0 multiplied with 1, 0, 0, 1, 0, 0, 0, 0, 0, 5. So 1 plus 5, it's going to be 6. Another step, orange one, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. This becomes 1. Another step, 1 multiplied with 1, 1, minus 1, 1 minus 1, 0, 0, 0, 0, 0. This is 0. And the last one will be this one. Yellow part, 0, 0, 0, 1, 1, 0, 0. It's going to be 0. Is there any other block? No, there is no other block towards right. Now we will move towards down. So Moving towards down, again 1 pixel down. So I will draw it in red now. 4 multiplied with 1 is 4. 0, 0. 0, 0, 0, 0, 0, 0. It will be 4. And this goes on. This goes on, and finally you come across a 5 cross 5 matrix. I will recommend you to pause this video here and try to solve the entire part. I will be, however, will be pausing here, and because you already know how it works. Similarly, if you want it for this pixel, it will be this block. Let me draw it in green. 0, 0, 1, 1, 0, 2, 0, 1, 1. It will be 1. Okay. This pixel 0, 0, 0, 2, 1, minus 2, 1, minus 1. It will be minus 1. And this pixel 0, 0, 0, 0, only 2, 1, 1, 2, 1, 2, 1, 1, 1. Okay. And this is how the entire output comes. So a 7 cross 7 image, if you are feeding a 3 cross 3 feature detector, your output is a 5 cross 5 image. Simple? Not that simple. Why did we move just 1 pixel to the right and 1 pixel to the left, to the bottom? Why? By default, we move 1 pixel. This movement of 1 pixel is called as strides. By default, my strides is 1. What if I'm using 2 strides? Again, strides is nothing but a hyperparameter that you use in your CNN architecture. What if we use 2 strides? Let's try to solve it. 2 strides. I will just format this entire graph. I have the same 3 cross 3 matrix, and then we will try to see what will be the output. So first block will be this. It will be minus 1, minus 1. Second block will be 2 pixels to the right. Green part 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. Last part will be this 0, 0, 0, 0, all 0, 1, 1, 0. It will be 0. So when you are using strides equals to 2, your output is going to be a 3 cross 3 matrix. So it all depends how many strides do you want to use. But what's more important is when you are using the convolution step, at least here, initially it was 49 pixels. Now using just 1 stride, you are able to get 25 pixels, almost 50% reduction in the number of pixels. But information remains the same. That is the beauty of CNN. Your information is remaining the same. Now let's just take this example and we will go ahead to the next step, which will be ReLu. This is the output to ReLu, and as I don't have the numbers here, I will randomly populate 1, 2, 3, 1. Make sure you calculate values for this, okay? Don't take these numbers because these are just randomly populated numbers. Minus 4, minus 5, something like that. Okay. Now, what is ReLu? Again, a refresher. ReLu is nothing but like this. This is ReLu. Y is equals to max of 0, x. So ReLu can never be negative. If x is less than 0, ReLu is 0. If x is greater than 0, ReLu is y equals to x. So the output of ReLu is very simple. The output of ReLu is nothing but the negatives will be 0, 0, 0, 0, 0, anything else 0. So this is your final output of ReLu. After ReLu comes your pooling step. Pooling. Okay, pooling step. Again, in pooling, I already explained you that there are multiple concepts. Let me just tell you about max pooling, and then I will tell you about average pooling. Again, in pooling, you have to define how much pooling do you want. Let's say you are defining a 2 cross 2 pooling. So what really happens is that it goes through the entire image 2 cross 2, 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 and it basically finds, if you are using max pooling, it will find the maximum pixel value. So let me just draw the diagram and then I will explain. First, second, third, fourth. Oh, let's not draw fourth, fifth, this one, and this one. So this is how your pooling goes through the entire 5 cross 5 image, and your ultimate output will be 3 cross 3. So max output of max will be as simple as this. What is the maximum value in this block? 6. Maximum value in this block? 3. 1, 1, 3, 1, 1, 3, 1. Similarly, what is average pooling? Average just takes the average. 6 plus 4 plus 1, 11 by 4, which will be around 3.75. 2.75. 11 by 4 is 2.75, right? 2.75, yeah. 2 plus 3, 6 by 4, which will be 1.5. 1 by 4, 0.25. 1 by 4, 0.25. 0.25. 2 by 4, 0.5. 2, 2, 4, 5, 3, 8 by 4, 2. 0.25. And 3 by 4, 0.75. This is the output of your average pooling. This is the output of your max pooling. Okay. Again, this 2 cross 2 is configurable. You can actually configure it in your convolution, in your neural networks, in your CNN code. Now just imagine you are using this pooling, okay, max pooling. Then comes your, okay, let me just cancel it out. After pooling comes your flattening. What is the output here? This one. Flattening will be simply this. So 6, 3, 1, 1, 3, 1, 1, 3, 1. And this will be nothing but this. Okay. This is the output of your flattening layer. And after that, directly you can create 9 neurons and then you can create your output neuron. This is all about your convolution steps. So if I quickly draw the diagram of convolution, I already have the diagram, but I love drawing it. Even if I don't draw it properly, just imagine these are multiple pixels. So just imagine this. What is this? This is nothing but a smiley. The image goes, let's say this is your conv layer. Then comes your ReLu. Then comes again your conv, then ReLu. Then pooling. Then comes your flattening. Then comes your fully connected layer. Then if you want to add another fully connected layer, you can. And then comes your final output. Okay, something like this. And then comes your final output, and this output will basically give you whether it is a this smiley or it is a this smiley. And this is a two conv layer network. This is all about CNN. Let me just show you the diagram as well. This is all about CNN. So in the next class, we will be jumping into the code part, where we will be talking about how to build a CNN from scratch. So we'll be taking some exciting examples to help you understand how CNN code works, and we'll also try to work on multiple use cases. So that's it about this particular video. In the next video, we'll quickly jump into the practicals part, which is the most important and most exciting part. See you. Hi, in this video we shall be talking about image augmentation. Now, what exactly is image augmentation? When it comes to machine learning or deep learning, the most critical task is to balance out the classes. Now, what exactly do I mean? Let me just give you a quick example with respect to machine learning, and then I will talk about image augmentation, which is a topic especially for images. Now, before talking about image augmentation, let's try to talk about a very classic problem in machine learning or deep learning, which is imbalanced dataset. Now, what do you mean by imbalanced dataset? Whenever we are working on some classification problems, whether it is a fraud detection case study or default or non-default or diseased or non-diseased. So whenever we work in classification problems, be it a binary classification problem or multiple class classification problem, the major issue with data is this one, which means our data is not balanced. You might have 1000 records, out of which probably 100 are fraudulent and 900 are not fraudulent. Now this is a clear case of imbalanced data set. That means your fraudulent data is just 10% and your non-fraudulent data is 90%. Now if you by default use this data to create a model, your model will be biased towards this particular class. Why? Because your model has been overtrained with class B, which is 900 records. For class A, it doesn't even have that much of information. It has only 100 records. So a better way to solve this problem here is to balance out the data. Whenever your data is imbalanced, in that we basically don't use accuracy as a metric, because accuracy is cursed in these particular scenarios. Instead of accuracy, what we do is we probably use classification report, or we check our confusion metrics. Classification report gives me a better understanding, because when I print the classification report, I can basically see an entire report for multiple classes, recall, precision, F1 score. Now, as a data scientist, I will majorly be focusing on the minority class. For this particular class, what is my recall, what is my precision, what is my F1 score? If that is low, my first priority to be enhance that particular score. And how can we enhance? By balancing out the data. Again, if you are new to all these concepts, this video will definitely explain you how to balance out data when you are working in machine learning area. So one concept in machine learning is going to be upsampling, and another concept is downsampling. Now, what is upsampling? Upsampling is simply when you have a data of 1000 data points, 100 is of class A and 900 is of class B. What we do is we synthetically create 900 records from that 100 records. There are some techniques like SMOTE, SMART ENN, or there is a method called as resample, which can also be used to achieve this task. This is nothing but you are synthetically creating the data points. Now once your data points are synthetically created, now you have 1800 data points. Now you can create a model, and now you can check accuracy. If your accuracy is good, that means your model is performing well. But I personally prefer with classification report all the time. So irrespective of any scenario, I always check classification report, based on which I take a call whether our model is performing well or not. And whenever you are solving a classification problem, your first priority is to increase the recall, precision, F1 score for your minority class. Now what is downsampling? Downsampling is like you have 900 and 100 records. You arbitrarily pick 100 records from here. Now you have 100 balanced data. Now you build another model which is M2. This is M1, this is M2. And now you check the output. So considerably, if I talk about upsampling and downsampling, upsampling is a better approach. Why? Because in downsampling, whenever you are selecting only 100 records from 900, that means you're discarding your 800 records, which is not a right way of dealing data, because there could be more information in that 800 records which we are just ignoring, right? So this is all about how to deal with imbalanced data sets. Now jumping on to our today's topic, which is going to be augmentation. Now why I haven't written image augmentation is because of multiple reasons. Now augmentation is nothing but, in layman's term, is the same thing that I explained. That means if you don't have data, you can augment and create new data. Now augmentation could be done for voice data, and it could also be done for image data. Okay, now let's try to understand voice data and image data. Voice data is nothing but amplitude versus time, and it is always a one-dimensional data. Let's say you are speaking, hello, how are you? That is a speech, right? Now, how can we augment voice data? That means if you have limited data, how can you recreate more data from your existing data? So there are some concepts like pitch shift, adding noise, removing the where you don't have any pitch, removing those areas, removing the empty speech data or something like that. And pitch shift is one of them. Yes, adding volume to it, that means increasing the dB or decreasing the dB. That means, again, this is also a pitch shift kind of concept. Now pitch shift is nothing but you are shifting the pitch, you are adding some volume to it or reducing some volume to it, adding some noise to the data, like hello, and you add some noise to it. That is also treated as a separate data to your models. Removing empty speech. Whenever we start talking, initial and at the end, basically the speech is very low, right? Those are kind of things where you can also discard. That is also possible. Now similarly, we'll talk about image. What exactly is image? Image augmentation, there are multiple techniques. There are techniques like tilting the image, like this side, that side, horizontal tilt or vertical tilt, whatever it is, vertical or horizontal tilt, okay. Another technique is adding noise, blurring the image. What else? There could be zooming in, zooming out, and there could be multiple other techniques which we use to recreate the data. See, just imagine you have an image like this. If you just add noise, if you add blur, or if you zoom in, zoom out, your pixel values will change, right? Images are nothing but pixels, right? Now your image is resizing, is also one of them. Resizing, let's say your initial pixel size is 500 cross 300. Now majority of your features are in this box. If you tilt it, now just imagine the data is tilted, something like that. So your majority of the features is like this. Now little bit difficult in understanding from the theoretical point of view. Let's quickly jump into our code part, where we will actually show you one of the examples by taking an image, and then I will show you how to do multiple image augmentation techniques. So here I am going to use a library called as 𝐓𝐢𝐬𝐬 for performing this task, and this is just for demo purpose. There are some libraries called as augmenter and data image augmenter, data image generator. Those are the algorithms or some libraries which can be used to automate the augmentation process. Okay, so let me just read this import, and then I'm reading a image which is this one. What is this image? If I just wanted to show you, this is the image. It's a cat image. Okay, now we will quickly jump into plt.imshow. Imshow basically is one of the methods inside your matplotlib to show your images. Here you can see it is quite visible that this image is somewhere around 1100 cross 1100 kind of image, right? If you want to see, you can right click the image and see the details. It is 1200 cross 1200. I just told you somewhere around that. 1200 cross 1200 image. So how many pixels do we have considering 1200 and 1200? 1200 and 1200. These many pixels I cannot name, but it's somewhere around 1.4 million. Yes, 1.4 million pixels. So the first technique of image augmentation is going to be rescaling. Now let's say I'm rescaling it to 150 cross 150. You can see even after rescaling, now this is a blurry image, right? If I just copy this image and let's say we will paste it in the paintbrush, and we'll copy this image and paste it here, you can see that this is the HD image, that means the 1200 pixel image, and this is the low clarity image, but the information is same. You can still identify a cat here, you can still identify a cat here. So it doesn't really matter to human eyes, right? But your pixel values are changing. Your pixel value in this image and your pixel value in this image are completely different. They are not same because of the resizing technique. When you resize, your clarity decreases, the color decreases, so your pixel value will also change. The way our human brain behaves, we are still able to identify the same cat in both the images. Exactly similar way neural networks will be able to identify the cat. So image augmentation is one technique where you can easily do all these things. Like it exactly works like the principles of human brain. I'm rescaling it further down to 50 cross 50. You can see how blurry it is, but I'm still able to predict it's a cat. So these kind of techniques we use to increase data, because when you get started with CNN, probably people take codes from Kaggle or GitHub and practice. But when you start working on a real life problem, probably you might not find the right data. So image augmentation comes as a rescue there. You need to use your image augmentation techniques, regenerate new data, and then build your CNN model. Some other techniques are flipping. So here I have done a horizontal flip. You can see it's still a cat, right? Nothing has changed. Vertical flip. Vertical flip, still a cat. Another thing is rotation. Here I am using rotations. You can also just change these numbers to rotate it 40 degrees, 20 degrees, 10 degrees, something like that. And even after rotations, computers treat it as different image, but they know that it's going to be cat, because you will be feeding the model that this is a cat, right? Because this is going to be training data. Similarly, adding noise. You can see here I have added noise. I think you can see some blurriness, right? Some dots, something here, dots. These are noise. You can also add more and more noises. And that's all about this particular session on image augmentation. I hope you understood the basics of image augmentation. We will probably be using these concepts when we start building our CNN models, only if we don't have data. So that's all about this particular topic. We'll see you in the next videos. Bye bye. Hi, in this video we shall be talking about one of the most common questions in terms of neural networks, which is epoch, batch size and iterations. What exactly are these terms? Why do we need more epochs to get a better results? All of these will be answered in this video, so we'll get started with it. Now this is a general idea on gradient descent. We already have been we have already explained gradient descent in another video, but let me quickly give you an idea about what exactly gradient descent is. It's an iterative optimization algorithm used in machine learning to find the best results. Gradient means the rate of inclination or declination of a slope. Descent means the instance of descending. So simply, what exactly is gradient? If I just start talking about this particular line, gradient is nothing but change in y with respect to change in x. Similarly, if you look at this graph, the gradient here will be change in y divided by change in x. Gradient here will be less, change in y with respect to change in x. Gradient here will be almost zero, right? So this is a general concept behind the gradient descent technique. The algorithm is iterative, means that we need to get the results multiple times to get the most optimal result. Okay, we'll not go deep into gradient descent. We'll quickly jump into our topic, which is epoch versus batch size versus iterations. I have already explained this scenario or this particular thing in our backpropagation class, but let me just quickly explain once again. Now if I just start drawing the neural networks, this is how my neural network looks like. Let's assume we have two hidden layers and then I have my output layer. So the connections are going to be like this, like this, like this. Something like this, right? We already know this is your input layer, hidden layer and output layer. Whenever you pass your data, this is the flow of forward propagation or forward pass. After forward pass, you get the predicted output and then you compare it with your original output or your test output, and then you find your cost function. If cost function is high, while backpropagating, you update your weights, right? So let's talk about epoch. One epoch is when an entire data set is passed forward and backward through the neural networks only once. Okay, now imagine this thing. What is an iteration? Let's try to understand that. Iteration, if I just quickly jump onto iterations. Before iterations, we'll talk about batch. Now, what is batch? Batch is total number of training examples present in a single batch. That means if you are passing the data, the first flow is first batch. Now imagine your data set is of 1000 records. Just imagine 1000 test training data. Okay, testing data could be 200 to 300, I don't care. This is your training data. Now if you define your batch size as 100, that means in your network, let's say I'm just drawing a small network. In your network, for the first time 100 records are passed. Then you get the output. Then once you get the output, you calculate the cost function. If your cost function is too high, while backpropagating, you update the weights of the neural network. And second transaction, again 100 record comes in. So batch size is nothing but the total number of training examples present in a single batch. In a single forward pass and backward pass, the number you have defined in batch size, those many records goes. X number of batch size, X number of batches completing one particular training set is called as one epoch. Now, if your training set is 1000 and your batch size is 100, how many times do you want to run to complete one full training cycle? 10. Training set length divided by batch size, 10 times. So 10 times forward pass, backward pass, forward pass, backward pass, that is one epoch. Now this 10 times which happens, one time, this is nothing but iteration. Okay, now iterations is the number of batches needed to complete one epoch. Okay, so I'm quickly jumping onto the epoch part again. So first time when your record goes through, if your batch size is 1 or 10 or 100, that entire flow, forward propagation and backward propagation, is called as one iteration. The number of iterations required to complete one training cycle is basically called as one epoch. So giving an example, if my batch size is 1000, sorry, training data is 1000, batch size is 100, and how many iterations are required? 10 iterations to complete one epoch. So if you define 100 epochs, that means you are running your neural network for 1000 iterations. So 1000 times your weights are updated. Weights are updated in backpropagation, right? Why we use more than one epoch? I know it doesn't make sense in the starting that passing the entire dataset through a neural network is not enough, and we need to pass the full dataset multiple times to the same neural network. But keep in mind that we are using a limited dataset, and to optimize the learning and the graph, we are using gradient descent, which is an iterative process. So updating the weights with single pass is not enough. Visualize it in such a way that neural networks are nothing but based on the concepts of our brain. Now what if I have 1000 images of an alien, a specific alien? If I just give you 1000 images right now and I will tell you train yourself in just 30 minutes, probably at the same point of time you will memorize it, but slowly that memory is not going to be consistent. 10 days, 20 days, 1 month, you might forget. So that is the reason why we basically pass our training set again and again and again to the neural networks to learn faster, to learn slower and learn better. Okay, that's why we need more than one epoch. So what is the right amount of epoch? Unfortunately, there is no right answer to this question. The answer is different from different datasets, but you can say that the number of epochs is related to how diverse your data is. Just an example, do you have only black cats in your dataset, or is it much more diverse dataset? So the complexity of data is all dependent based on the epochs. If it is too complex, you probably need more epochs. If it is easier data, then you need less number of epochs, right? That's all about iterations, batch size and epoch. A small example, let's say we have 2000 training examples. I will recommend you to pause the video once I read through the question, answer, and then probably you can unpause the video. So 2000 training example we have. We can divide the dataset of 2000 examples into batch of 500. So how many iterations are required to complete one full training cycle? 2000 by 500, which is 4. Iterations equals to 4 in one epoch. Completion of 4 iterations is nothing but completion of one epoch. Then it will take 4 iterations to complete one epoch. When batch size is 500 and iteration is 4 for one complete epoch. Now in this example, if I tell you my epoch is 100, how many iterations will you run? 100 multiplied with 4, which is 400 iterations. How many times weights are updated? 400 times. The number of iterations, those many number of times your weights are updated. That's all about this topic. This is a very important topic as well. Many people get confused by these terms. So next video we'll quickly jump into the CNN code. Hi. In this video, we shall be jumping into our first CNN code. So here we are going to talk about a basic MNIST dataset, fashion dataset, but slowly we'll also talk about some other use cases as well. I also have an X-ray image classification, which will probably for the next video. So we'll quickly get started for this particular case study. In this case, as we are just jumping in, this is our first exercise in CNN. We are using a toy dataset. So which dataset we are using? We are going to use fashion MNIST dataset. Fashion MNIST dataset. So this is one of our toy datasets, and this dataset is also present in multiple sklearn library and other libraries as well. So let me just quickly talk about the MNIST dataset. Now this dataset has probably 9 or 10 classes like trousers, coat, multiple classes are there, and these are all grayscale images, right? Grayscale images, and we will be feeding these images and we'll be creating our first CNN model. In case you are not aware of ANN, probably you can also get into ANN and try to understand how ANN works. But anyways, CNN and ANN are completely different. They are not relevant to each other. So we'll be focusing more on the CNN part. We'll get started with it. Here I am running all these libraries. I'm importing all these libraries. TensorFlow. I am using Keras, which is a wrapper class on TensorFlow. And okay, let me just explain you these libraries because this is the first class on the code part. Let me just explain it. TensorFlow is nothing but a deep learning framework. Keras is nothing but a wrapper class. Internally, Keras also uses TensorFlow as a backend. Okay, so if you learn using Keras, you can simply implement the TensorFlow codes as well, nothing to worry about. But in this case, we will be focusing more on the Keras part. Normally, when we use our classification problems, right, or we use our regression problems, we probably use decision tree classifier or random forest classifier, right? Or else in regression we use linear regression, something like that, right? So here in neural networks we will be using sequential. Why? Because neural networks is always sequential in nature. You have input layers, hidden layers, and then output layer. And here I'm using dense layer because ultimately CNN is nothing but conv pulling, flattening, fully connected, and then comes your output layer, right? So your output layer and fully connected layer will be using a dense layer. That is why we are using dense. Dropout is something called as dropout is a regularization technique. We can probably have a separate video on that. But dropout is normally a regularization technique which is used in each and every layer in order to get rid of the overfitting problem. Normally we use a dropout of 0.2 or 0.5 or 0.8, and it depends on scenario to scenario. We will be using flatten. Flatten is also present inside your Keras layers, and here we are using conv 2D and max pulling 2D. As I have already explained you, we have three: conv 1D, conv 2D, and conv 3D. This is nothing for videos, this is nothing for images, and this is nothing for audio. Audio is nothing but one-dimensional data, right? Something like that. So we are using conv 2D and we will be using max pulling 2D. Here I am mounting the drive, but anyways I don't need to mount the drive because I am already using an external library to get the data, right? So I don't have data on my local space. Here I have defined my variable called as number of classes because in this case study I already know that there are 10 classes. I have defined my batch size as 64 and epochs as 24. Okay. Image rows and image columns equals to 28, 28. So this basically means that I am defining that my input image should be a 28 cross 28 image. What does this mean? So normally when we define our CNN layer, basically when we feed our input image, our image could be a very HD image, right? It could be 1920 cross 1080, or it could be 500 cross 300. So whenever we are defining images, we are using images for CNN models and all those things, different image will have different dimension. There is no doubt about it. Nobody will be in sync with each other. They will have their different configurations. So it is always better to normalize it. Okay, so that is the reason we are asking each and every image to be a specific dimension. In short, we are resizing all the images to 28 cross 28 format. Why 28 cross 28? This is just my, I have done it. In case you are using a data set, based on your computational limitations, you have to define this input shape. If your computer is too strong, your processors are too strong, then you can probably increase the shape and size as well. But just make sure if you increase the size, then your models will take more time to run. As simple as that. So in short, here I am defining my input image dimensions. Here I am calling the fashion MNIST and loading the data. So my training and test data will be loaded here. Run this. Now this is basically, it is downloading the data from the MNIST module. Fashion MNIST is what I am using from Keras datasets. This is present inside Keras. This is my training data. This is my testing data. So my training data has 60,000 data points. Now, question. Now my training data is 60,000. My batch size is 64. How many iterations do we need for one epoch? How many iterations? It will be 60,000 divided by 64. Around 938 iterations. Okay, so 938 iterations for one epoch. So for one epoch, these many times the weights will be updated. For 24 epochs, multiplied with 24. These many times the overall neural network weights are going to be updated. Okay, so let me just remove it. We'll go back to the code again. Length of y, length of y train, all these things. So here I am reshaping my data. Here you can see my data is now like this, right? Here I'm reshaping my data into the image calls. What is my image calls? 28 cross 28. Now if I run this, now my input shape is 28 cross 28 cross 1. Okay, simple. Here what I'm doing is I'm calling my training data, and here I'm doing xtrain equals to xtrain by 255. Okay, one more concept here. What exactly are we doing here? We are doing xtrain is equals to xtrain divided by 255. Why 255? If you don't remember, images are nothing but pixels, right? And pixel values ranges from 0 to 255, where 0 means black, 255 means white, right? What we are doing here is, let's say here it is 15, here it is 200, here it is 0. Your final output will be in this pixel, it will be 15 divided by 255. Here it will be 200 divided by 255. So we are scaling down the value. So this is nothing but feature scaling technique. So I'm scaling it down, and now my data looks like this. After that, here I'm converting the class vectors to binary class matrix. Similarly, we are doing one-hot encoding here. This is where the fun begins. I will just add a text here. CNN code begins. CNN code. Okay. So we are calling the model sequential. Model equals to sequential. Like in machine learning, we used to call, right? CLF equal to decision tree classifier. That's what we are doing here. We are calling the sequential classifier. My number of classes is 10, which is we already know about it. Now this is the main piece of code where we are, basically when we are calling our hidden layers and all those things. You can see I'm calling conv2d, max_pool2d, conv2d, max_pool2d. So this entirely is nothing but a 2 hidden layer network or 2 convolution layer. Okay. Now we will try to understand the different numbers here. If you don't remember, we had talked about a CNN example, right? Where we talked about, all these things. If you just don't remember, I can quickly open my CNN example. Okay, CNN example, this one, just a refresher. This is what we had, studied, right? Convolution and then ReLu, all these things. Remember this thing, feature detector? I told you, right? We don't define one feature detector, we define multiple feature detectors, and the numbers within the feature detectors are arbitrarily filled up. This 32 is nothing but the number of features. What is the feature detector shape? 3, 3, which basically means 3 cross 3. Activation equals to ReLu. I already told you, as it is a CNN network, ReLu is by default attached to the convolution layer. Input shape equals to input shape. So here I am passing my input shape, which is 28 cross 28 cross 1. Okay. Again, why 28 cross 28 cross 1? Why not cross 3? Because this is a grayscale image, right? Grayscale images always have one channel. Color images always have 3 channels, right? RGB, red, green and blue. So we are just passing the input shape here. Here I am calling the max pool 2D. What is max pool 2D? Now if this is the output of ReLu and this is the output of max pool, so 2 cross 2, 2 cross 2, 2 cross 2, and here we are defining the pooling is 2 cross 2. So this is nothing but your conv max pooling, conv max pooling. So this is a two layer conv layer network. After that we are calling the flattening. What is flattening? Flattening is nothing but conversion of a n cross n matrix to a one-dimensional matrix, so that that one-dimensional matrix can be converted into the neurons and that can be converted into the output layer, right? So we are using flattening here. After flattening, this is where the fully connected layer comes into picture. After flattening, then comes 128 neurons, then comes another dense layer, 64 neurons, and then comes your final layer, which is your output layer, which has 10 neurons, because 10 classes. If you have 2 classes, then 1 neuron. If you have 3 classes, then 3 neurons. 10 classes, 10 neurons. This is how the CNN architecture looks like. If I just want to draw this architecture, this is how the architecture will look like. I have input image, then comes conv, ReLu, pooling, flattening, and then comes, after flattening comes 128 neurons, and then comes 64 neurons, and then comes your final output layer. And then this is your final output, this is your input. So this is your network, 2 conv layer network. Okay, this is your conv, pooling, flattening and fully connected layer, right? Now everybody understood, and now we'll come back to the number of filters. Number of filters again is a hyperparameter. The more number you increase from 32, 64, 128, 256, computational power increases, right? It will take more time to process, it will be better as well. Again, to improvise a model, you can also add more conv layers. Okay, similarly, we are using 128 in my dense layer, then 64, and then number of classes. We'll run this code, and after that we'll move on to the compilation part. Here, define compile to minimize categorical loss, use ADA delta optimized and optimized to maximum. Use some optimizer to optimize. Okay, now here we are compiling our model. My loss function is categorical cross entropy. If you don't know, this is basically the loss function for multi-class classification. Okay, now in multi-class classification, your loss function has to be categorical cross entropy or sparse categorical cross entropy. If you are using a binary classes, it could be binary cross entropy. Okay, similarly in your final layer, if you are using a binary classification, then it could be a sigmoid function. As you are using more number of classes, it is softmax. Optimizer, here we are using Adam optimizer, but it is not the best optimizer. There are many other optimizers like SGD optimizer, RMS prop optimizer, so you can also test it out with your code later on. And then here I'm calling the model.fit, passing my training data. Batch size is 64. This is nothing but 64. This is nothing but 24. And this is nothing but verbose. I honestly speaking, I don't know the meaning of verbose. We'll probably check out that. If you know the meaning of verbose, let me know in the comment section or let me know as a feedback. And this is nothing but validation data, which I'm passing my testing data. Now if I run this, this is where our code gets started. We are running it for 24 epochs. My training data is 64,000 if you don't remember, and my batch size is 64. That is the 60,000, and my batch size is 64. So total iterations in one epoch is 938. That is the reason you are seeing this number 938. So on an average, it should take 24 epochs into 8 microseconds or milliseconds. 8 into 24 should be around 3 minutes. So let's try to wait and see the output. While it runs, let me explain you all these features, all these things. So whenever we run a neural network, we basically, you can see it is printing you loss. Why? Because you have defined your loss function. Okay, you have also defined metrics as accuracy, so you are getting accuracy. You are also getting validation loss and validation accuracy because you have passed the validation data as well. So let's try to wait for a little minute and then we'll quickly jump on to the next part. I think it's done and dusted. The code is ready. Our next step is just to print and show you the training accuracy and the test accuracy. That's it. So 2 more minutes and the code will be done. So this will be all about this CNN example, and in our immediate next video we shall be talking more about one use case related to the healthcare industry. So we have X-ray image classification as well, X-ray images of normal and diseased patients. See, it really doesn't matter about the use case. If you can build a basic CNN model, you can easily build other models as well. The major task is data collection and augmentation. Mostly if your data is proper, augmentation has been done properly, then you might not face a huge problem in the CNN model building part. Model building part, if I can give you this code, you can simply run these codes. We can also have codes related to hyperparameter tuning, so you will not face issues with these kind of codes. Okay, the epochs are almost done, and you can see finally my accuracy, my training accuracy is almost 98% and my validation accuracy is almost 90%. So if I just draw my graph from a scale of 0 to 0.9 and 1, you can see it all started from 0.8, right? So the training accuracy is something like this and test accuracy is something like this, right? So if my test accuracy would have been somewhere here, then I could have easily told that we are facing an issue of overfitting. But now test accuracy is almost 90%, training accuracy is almost 98%. So somehow there is a gap, but I don't think, I think it's okay. Maybe with minor tweaks we will be able to fix it up. Now going back to the next code, which is plotting the test loss and the test accuracy. So this is my training accuracy and validation accuracy. You can see on the scale of y-axis it is showing from 0.8, so you can see a larger gap. But if you look at the scale from 0.0 to 0.975 or 1, I don't think there is a huge gap. Now comes the most important part of this video, which is going to be model summary. So this video we will be covering in the, we'll not be covering in this video, we'll be talking about more about this model summary in the next video. Hi. So in the last video, we basically showed you how to run the CNN code, and we were almost in the model summary part where we stopped the video. Now in this video, we shall be talking more about the model summary part. What exactly is this? Model summary is nothing but it summarizes the model. It basically tells you how many layers you have used, what are the different attributes, how much did you change the pixels, how many trainable parameters, all those things. Now a quick refresher about the previous example. Like here, when we ran through this example, I hope everybody remembers that we did this on a 7x7 image which was 49 pixels, and then at the end of convolution we ended up with 25 5x5. Then we did pooling, then we ended up with 3x3, and this is how things happened, right? So here we will be talking about all these things. Now have a look at this. The first conv layer is basically having 26, 26. Why? Now just imagine, we don't have to imagine, sorry, we have taken our input image as 28x28. Agreed? How many filters did we took? We have taken 32 filters. Filter size was 3x3, right? Now when we are using a 3x3 filter on a n×n image with strides 1, your output is always n-2x n-2. Okay, first case scenario, 7x7, your output is a 5x5 matrix. So if you take 9x9, it will be 7x7. So that is the reason the output of your convolution is going to be 26x26. So that is the reason here you can see 26x26x32. Agreed? After that, your max pooling is again cutting down the total number of pixels to 50%, right? Let's say you have 4x4 image, and on the 4x4 image you are using a 2x2 pooling. That means your output will be 1, 2, 3, 4. Your output will be a 2x2 image. 50% reduction. That is the reason 13x13. 32 is the number of filters. From here again you use the convolution layer, so 11x11. From here again pooling, again 50% reduction, so 5x5. After that you have 800. What is this 800? Now this 800 is the simplest thing to understand. What is flattening? Now if this is your output of the pooling 3x3 image, this is nothing but you convert it into 9 boxes, right? One dimensional. So this is 5x5, which is 25, multiplied with 32, which is 800. Okay, 128, everybody knows in our fully connected layer we used 128 and then 64, and final one we used 10. So now everybody is clear with these numbers. What are these numbers? We'll talk about that now. To understand these numbers, this is the formula that you should refer. Parameters in a conv layer. So for this layer and for this layer, you will be using this formula. So let's try to use this formula for the first layer. For the first layer, this is nothing but bracket bracket shape of width of filter. How much? 3. Cross shape of height of the filter. 3. Cross number of filters in the previous layer. There is no previous layer, So I will just consider it as 1 plus 1 multiplied with number of filters. How much? 32. So what is the number? 3 cross 3 is 9. 9 plus 1, 10. 10 multiplied with 32, which is 320. So we have 320. We will move on to the second conv layer, this conv layer. Again, shape of my width of filter 3 cross 3 cross number of filters in the previous layer 32 plus 1 multiplied with number of filters in current layer 32, which is 3 cross 3 9. 9 cross 32 is 288. So this is 288 plus 1 multiplied with 32, which is plus 1 is 289 multiplied with 32 is 9248, which is this number. Okay, similarly for these three we will be using this parameters in the fully connected layer. All these are your fully connected layer. Okay, now for this scenario, what is the formula? Current layer multiplied with previous layer plus 1 into C. Current layer, how much? 128 multiplied with previous layer, which is 800 plus 1 into C, which is current layer, which is 128. Now if you just multiply it, 128 multiplied with 800, which is 102400, which is 102400 plus 128 plus 128 is 102528. 102528, and this is this number. Similarly for this one, current layer, how much? 64 multiplied with previous layer 128 plus 1 into current layer 64. So 64 multiplied with 128 is 8192 plus 64 is 8256. So 8256. This is for this one. And for this one, it is current layer, which is 10 multiplied with 64 plus 10, which is 640 plus 10, 650. So these are the explanations of how these parameters are generated. These are all your different parameters in your neural network. In this case, as we are not using any dropout regularization, all your parameters are trainable parameters. There is no non-trainable parameters. That's all about this particular video. In case you need more details about it, probably what you can do is, there are many blogs related to this particular concept. You can go through it, but I'm pretty much sure this video is more than enough. So next video will be quickly jumping into our X-ray image classification. See. Hi, in this video we shall be talking about a very important case study which is related to healthcare industry. So this is nothing but a X-ray related image classification model. So what I have right now with me is X-ray images of multiple patients, people who are suffering from pneumonia and people who are not suffering from pneumonia. That's going to be one of the case studies, and the code is almost going to be similar to the previous code that we talked about, which was on Fashion MNIST, but let's see how the code looks like. So anyways, I'll not be running the code because if I start running it, it will take a lot of time to process, but I will be giving you this code so that you can run it by yourself. So here we are importing the TensorFlow library. TensorFlow is basically a framework, and here I'm checking the version, which is 2.6.0. So let me just run these two commands, and quickly we'll jump into the next commands. Oh, 2.8 right now. So automatically, as I'm using Google Colab, it has automatically upgraded the TensorFlow. So here I am mounting the Google Drive. And yeah, I mean, we'll not be mounting it, but this is how it is. And on the go, I'll also explain you how the data looks like, how the codes has been written, each and every line will be explained. So I'll be passing on this information to you, this zip file, which you need to keep it in your My Drive location and then just unzip it and then use it. That's it, as simple as that. So I'll quickly join. As you can see that the first type, you can see one is normal and one is opacity. So these are the two different categories that we have right now, and based on these two categories we are going to create our image classification problem. This is a purely binary classification problem. We have normal patients data and the people who are suffering from pneumonia. Okay, so moving ahead, I'll also show you the images as well. I have printed down the images as well. Going down, this is where we have started importing the NumPy, the Matplotlib, computer vision libraries. In this code, I am setting up my training data directory. So data directory equals to train. Similarly, my testing data directory will also be set. Categories we are defining here in a list. A list contains the two different categories that I have. So these are my Y variables, normal and opacity. Initializing the category of classification. So here, once you have unzipped your file, you can also do ls space the folder, which will basically tell you how many subfolders do you have in this folder called as a test. ls is nothing but list operation, is basically a Unix based command, but this is how things work. Here I'm converting the data into a grayscale image because normally X-ray images are grayscale. So in order to make sure that the images are grayscale, and if not, we will converting the data into grayscale image, because the moment you convert a data into grayscale image, first of all, you are reducing the dimension from 3 channels to 1 channel, which makes it even easier to process the files, and computation time will be less, right? So here it's basically for in categories, for all the categories data, taking the data from that data directory path and then using the cv2.im read, and then I'm just printing the data. This is how the data looks like. Now initializing the size of the image so that every image should be same dimension. So here the same concept comes in where I was explaining in the previous CNN example, that when we are dealing with the image classification problem, we could have multiple images with different dimensions. One could be 1920 cross something, one could be 500 cross something, one could be something like this, one could be something like this. To normalize it, here what we are doing is we are just passing 100 cross 100. So each and every image will be now 100 cross 100. If it's a bigger image, it will be resized to 100 cross 100. If it was a smaller image, it will be enlarged. And here, image after resizing and grayscale, this is how the image looks like. I'm not running the code because it will take a lot of time, but as you can see, the images are basically changed. Here it was around 1400 cross 1600. From that, it has been compressed to 100 cross 100. Here I'm reading my training data, and here I am defining the function for training data according to the categories, converting the image into grayscale with resizing the image into 100 cross 100, converting into NumPy arrays. So very simple piece of code. If you are not confident on this type of code, you can also reuse the exact fashion MNIST data, or else what you can do is you can simply go to the web, just search for cat dog classification. There will be tons and tons of Python notebook. Take that notebook, take the data which I am giving for the X-ray part and directly feed in. You will be able to create your base model as well. So nothing to worry about. Which means that computer vision or your CNN codes are pretty much reusable. Here I'm creating the training data, and here I'm printing my length of the training data, which is 4192. Here I'm shuffling the data so that shuffled data goes into training data and test data accordingly. Here I am splitting the feature and labels. For features label in training data, I'm just doing x dot append features and y dot append label. That means the features goes into my x data. Features basically means x variable data, and the label or my dependent variable goes into my y variable. As we already know that images, when we are feeding it to our CNN model, it is always expected to have 4 dimensions. That is one of the reasons why I am adding one more dimension here, so that it can be compatible to be fed into our neural networks. So I am doing reshape -1 image size comma 1, as we do for training data, similarly doing for the validation data as well. So simple, same piece of code for training data, same piece of code for validation data. By calling this validation data function, we are able to generate the validation data, which is of 1000 data points, 1040. Again, shuffling the data, we will be moving on to the main piece of code, which is the convolution part. So far, till this line, we have prepared the data. Training data, test data, reshaped it to 4 dimensions so that it can be fed to our neural networks. And now comes the most important part, where we will be initiating our classifier. So here, importing the library for training the mode and training the model and adding the neural networks. So we are going to use Keras model sequential, dense dropout activation flattening, and we are also using conv2d and max pooling 2d. So why conv2d? Because it's a image based classification model. If time permits, we'll also do some CNN 1D related videos in future, but yeah, for the time being, this is it. What exactly is this step? If you know, pause this video, try to answer it. This step is nothing but it's a feature scaling step. So normally our pixel values ranges from 0 to 255, right? 0 means black and 255 means white. So in order to scale it down between 0 to 1, we are dividing it with the largest value, right? So this is what is happening here. In order to scale it down to 0 to 1, scale it down to a scale of 0 to 1, we are performing this step. Done? Then you can run it. Once done, you can check the x dot shape is basically the data points, size 100 cross 100, comma 1. 1 is basically for the dummy feature or the dummy dimension. Similarly, this is my validation set. Now comes the most important part, which is our model creation part. So here we are using sequential classifier, which is very clear. Now let me just try to take a screenshot of it. Hardly it should take 2 minutes, and then we'll open Microsoft Whiteboard. There we will be okay. We do have, how do we create? Oh, clear canvas. Okay. How do we increase it? Okay, something like that. Okay, now this is how my data looks like. Now we'll be explaining this data here. So we already know that we are going to use sequential classifier, right? After sequential classifier, what we are doing here is we are creating our conv2d model. Okay, 64 is the number of filters. 3 cross 3 is basically my, what is the dimensions of the filters or feature detector, something like that. Input shape is equals to this. This is basically my input shape, and this together is my conv plus ReLu. After that, I'm calling max pooling 2D, where my pool is basically of 2 cross 2, right? And then I'm calling dropout 0.2, which basically means See, when you start creating a model, you usually don't do dropouts. You create your models and then check how your model behaves, and then you add the dropouts. Normally we don't use dropout, but initially when we get started with our code, we basically don't use dropout. But when we see some overfitting situation, we probably add dropouts in each and every hidden layer, and that number depends from, data scientist to data scientist. It depends from case to case. But the numbers are very clear. These are why the numbers are used. And there is no such hard and fast rule to use 64. People start with 32. You can also use 64, 128. Nothing to worry about. Similarly, the second model is also, the second convolution layer is also built with the same, not with the same. You could have done using the same filters, but here we have used 128 filters and 3x3. Activation is still ReLu and pool is 2x2. Another conv layer, similar configuration, but we are doubling the filters, and then we have the flatten layer, then the fully connected layer with dropouts, and the final output layer with dense one. Dense one basically means that this is a binary classification problem. Simple. And activation function we are using is Sigmoid. That's how the code looks like. Moving on to the next code, which is going to be the model.summary. Now everybody remembers model summary, how model summary is calculated, how the number of parameters are calculated. In case you don't know, probably you can watch out the previous video which talks detailed about how these calculations happen, but I'll give you a small idea about the first number, why 640 and why 9898. So just imagine this way. This is how my data looks like. Okay, my con 2D is basically okay, it's not working, but it's okay. So let me explain you this thing in MS Paint. Now imagine this way, your first input is always 100 cross 100, right? This is what we have defined in the network. On 100 cross 100, if you're using a 3 cross 3 filter with one stride, then your output has to be 98 cross 98. That is all about this number 98 98. 64 is nothing but the number of filters that we have used, right? Why this param is 640? Why 640? Now this param is following this formula. Number of the size of your filter length multiplied with width plus 1 multiplied with the number of filters in the current layer. Okay, 64, which is nothing but 9 plus 1 10 multiplied with 64, which is 640. Similarly, conv layer in this one, why it is 73856? This is nothing but 3 cross 3 multiplied with filters in the previous layer, which is 64 plus 1 multiplied with 128. So if you just calculate this number, should be this number. 3 cross 3 is basically 9 multiplied with 64 is this, plus 1 multiplied with 128, which is 73856, and that's this number. So this is how your model parameters are calculated. And finally, once your model is ready, then you simply have to call the compile method and then call the fit method. Compile method, here again it's a binary classification problem, so we are using binary cross entropy. Optimizer, we are using ADAB because of no reasons. You can choose RMS prop or you can perform your hyperparameter tuning part. Matrix equals to accuracy. Here I'm passing my X and Y data. Batch size is this, epochs is this. Now all these things are done, and then if you run, then your epochs will be done. And after your model is ready, after this your model is ready. If you want to save your weights, you can also save using the saving the model part, which is model.save. Pass a .html name to it and the model will be saved here. Why are we saving models? Because we can save models and reuse it later, so that we don't have to retrain it again and again and again. Our next few pieces of code are basically for the testing part, where we are calling the libraries, we have defined the categories, and here we are preparing for image for the prediction part. We are loading the model, and then we are passing a singular image, and then we are predicting it. You can see for this particular image, which I cannot show you right now, which could be a X-ray image itself, it is getting predicted as 99% chances are that the image is having opacity, which means the patient is having pneumonia. That is the whole idea. And then this is how the image looks like. This is the X-ray image that we are testing on our existing model. That's all about this particular case study on X-ray image classification. Honestly speaking, if you start writing your first piece of code in CNN, you can definitely reuse the same piece of code for any kind of work. You just need to take that and fine tune it. So there will be few other concepts as well, like transfer learning, pre-trained models, which we also come across on multiple scenarios where our individual models are not performing well. So those are some very advanced topics, and that's all about this particular case study on X-ray image classification. And see you in the next video. If you liked it, please just follow me on YouTube, and that's it. Thank you.